Hello everyone, my name is Autoencoders. I'm a professor here at this university teaching speech processing courses. And it's a great pleasure and honor for me to introduce a big friend, Professor Bhiksha from CMU. Bhiksha is a fellow of IEEE, and his extensive CV is very much longer than I can quote here. I'll just tell you that he has made seminal contributions in many areas of speech and audio processing, as well as machine learning. And in speech, he started by being known for his contributions, his key contributions in the area of robust speech recognition, missing features, automatic discovery of units, things that now seem so familiar to us. At the time they were not. They were really important and extremely innovative. He also made lots of contributions in the area of speech separation, speech enhancement, more audio processing, and then in machine learning he did a lot. In deep learning, as you'll see, he has made very innovative contributions, and his course of machine learning at CMU is the biggest course there, taken by over 400 students, and it's the materials of the course are being followed in several universities in the US, but all around the world. And his open data science has taken these materials also for their courses. So we think it's fantastic. We've been having the same lecture, though constantly improved. He is always adding to the lecture for a number of years now, and it's always been ranked as one of the favorites by all the attendees of this course. So hope we enjoy it. Thank you, Bhiksha.
Thank you very much. So that was very flattering. Thank you. Good morning, everybody. For the next 3 hours, I'm going to be talking about things that you're familiar with. Nothing I will talk about in the next 3 hours is important. So you can kind of relax, but maybe it will give you a little bit of insight on the things that we do when we are working with neural networks. Let me see it. This works, yeah. Of course, things should work, right? What has happened? Page down. Yeah. Amazing. So we're going to have another this slide, whatever it is, because at least here it works. Yeah.
Maybe after putting it show yes, then press it, then try.
No.
Are you sure?
Yeah, my laptop is it's okay.
Maybe to close the application and open it again.
No, it's so part of the job of doing lectures is the entertainment provided for free by Microsoft. So just in case. All right. Hopefully the slides will advance when I try. But here's what we're going to be talking about. We're going to be talking about historical perspectives. What is a neural network? What it can model and what it actually learns. Now, all of you have been working with neural network toolkits. You probably think you understand a whole lot of the whole process behind it. Let's see how much of it you actually know. So I'm Bhiksha. I'm a professor at the Language Technologies Institute at Carnegie Mellon. And that is our lovely university out there. It looks very pretty. In this picture, if you actually went and saw the latest constructions, they're quite ugly. Anyway, so let's start with what is a neural network. At this point, all of us are very familiar with why we are working on neural networks. They've just taken over all of AI. And you pick the area whether it's, the topic under artificial intelligence, whichever direction, speech, images, text, you name it, neural networks have taken over. And they are basically the state of the art by a very large margin. So but when did the whole thing start? It turns out that the takeover by neural networks is actually very recent. So I can show this slide because this is where I think 2016 is where the world changed. So prior to that, we were working, for example, on speech recognition for over 50 years, 70 years from 1950. And in 2015, if you tried to use Siri, you usually got very funny responses. And then in 2016, for the first time, an artificial intelligence, a speech recognition system outperformed human beings on a speech recognition task. This was also the first time that we actually had a large-scale deep neural network-based speech recognition system. And this was achieved mainly because we were using neural networks. Now, of course, the performance is much better. It's not just this one task. On any speech recognition task, if you've got the training data, if you're able to train your neural network, the neural network will outperform human beings on the same task. Or machine translation. In this was 2016 October. If you use Google Translate to translate English to French and then translated the French back to English, what went in and what came out would be very different. So we mostly use Google Translate as a joke, as a party joke. We'd sit there and we'd be translating things back and forth and laughing at the outcomes. And then in November, suddenly the thing didn't stop being so foolish. It actually began working. What happened? Google switched to neural network-based machine translation systems. And these days, you use Google Translate even if you're an expert translator. If you're even professional translators will start off with the first cut using these tools because they are so good. They're better than human beings, most humans anyway. So this was made possible by neural networks. Or image analysis. So this is, I stole this from the web, so I don't know if this is actually authentic, but this is the kind of performance that your neural networks routinely do. If you give them a complicated image of this kind, they can segment out and identify every object in the image. Again, this is post 2016. It was not possible earlier, and also only because of neural networks. Or playing computer games. Or playing games, not computer games, playing games, hot games like chess or Go. We have long been considered the domain of human expertise. When people began speaking of intelligence and artificial intelligence, the first serious task they looked at was chess. And it was 1995 or thereabouts before computer chess games actually began beating human beings on a consistent basis. But we figured that chess was done. Go was the real challenge, because in chess, there are about 10 raised to 120 game states. Go has 10 120, and Go has 10 raised to 180 game states. So it's 60 orders of magnitude more complicated than chess. And we thought that, computers are never going to beat human beings. And then in 2016, AlphaGo came out. AlphaGo beat the world champion Lee Sedol at that time. These days, there are actually versions of AlphaGo, which can start from zero without knowing the rules of the game, learn to play the game, and beat the world champion, and they can do all of this in a few hours. So that's how good the whole process has become, and that's because of neural networks. So, image captioning. All of you have been looking at examples of images not merely being captioned, but being generated. Computers writing enhanced stories. They can write. Rita's put out a poetry book, which has been produced entirely by an artificial neural network, no human interference. And all of these are possible these days. The first paper along these lines is also around 2016, where you have, you can't really read it on the screen, but you had all of these images being automatically captioned by a neural network, and these captions were very accurate. So I think I can try to read it out here. It says the boy is doing backflip on a wakeboard. So that's the one on the top extreme right. Or man in black shirt is playing guitar, the one on the top left. As you can see, these are very accurate, authentic captions. This was 6 years ago. Right now, you can give them something of this kind and the program will write you an entire story around it. All of this was unimaginable 7 years ago. There was no way, in fact, the very task of captioning images automatically is something people were dreaming about for decades. We didn't think it was possible before neural networks began doing the job. And so a variety of other problems. Image analysis, natural language processing. You saw Slav Petro's talk yesterday. It was phenomenal. That's the kind of stuff neural networks can do. And Slav himself, as Slav himself told you, only 2 years ago, doing something of that kind automatically seemed a pipe dream, right? That's how far these things have come. Stock markets. Every company that's playing, our investment firm that's playing on the stock market is using neural networks these days to make their predictions. And how fast have things progressed? If you're a hedge fund, or if you're one of these companies that do very fast trades, you have milliseconds to make a transaction. So 5 years ago, you didn't think neural networks were going to do the job because in the time it took the neural network to perform a computation, your competitor would outbid you, make money, and you would lose money. They're literally looking at milliseconds in lag to perform their bids. These days, everything is being done by neural networks. So, they're basically the basis of everything AI. And here's the biggest need to be learning all about neural networks. 5 years ago, if you had neural network skills on your resume, it was a plus. If you didn't have it, you'd still find a job. These days, if you're a computer science person and even an electrical engineer for that matter, and you didn't really and don't have skills on manipulating and working with neural networks, you're not even going to find a job. So that's how important it's become. So what are these things, right? All of these crazy, fancy, magical things that neural networks are doing. In each case, all of the tasks that I spoke about, they're being performed by a box, some black box which take in an input and produce an output, like speech recognition. There's a box that takes in a voice signal, it produces a transcription. Or it takes in an image, it produces a text caption. Or a game state, it predicts the next move. What's in these boxes? What makes these boxes do these jobs so really well? To understand that, we have to go back and look at the origin of all of these operations. Now, playing games, writing stories, all of these are fundamentally human tasks. You don't find dumb machines previous to these. You don't find inanimate objects or even stupid animals writing stories. So these are things that start from the human brain. The processes in the human brain are what make these things happen. So to understand how these operations can be performed, maybe we want to go and look at the seat of all intelligence, the human brain, or even before that, the process of cognition. Here's what humans can do. We can learn, we can solve problems, we can recognize patterns, we can create, you can just be having a shower, there's no input at all, you're just standing in one spot, your brain is running, you come up with ideas, you come up with thoughts, you can cogitate. So all of these things are happening inside your brain. And obviously all of these other tasks you're looking at, like captioning images or recognizing speech, they're also happening in there. So if you want to do these tasks, it makes sense that we should be emulating the brain, right? And the problem is this. If the brain, as Marvin Minsky says, if the brain was simple enough for us to understand, we would be too simple to understand it. So that doesn't stop us from trying. And so people have been trying this for about 2,400 years at least at this point. The earliest models of cognition go back to Plato, and so this is this famous, what's this painting, the School of Athens. And I think the two people in the middle are Aristotle and Socrates. So anyway, so this goes back to, people have been wondering about how the brain works for a very long time. And the earliest models based on what are called associationism. So it was originally hypothesized at least no later than 400 BC. And people have been working on that idea for 2,300 years. So David Hume in the 1700s, Ivan Pavlov, everybody knows about Pavlov's experiments with dogs in the 20th century. All of them are working on this notion of associationism. So what is associationism? The idea here is that the brain stores its percepts and makes its inferences through associations. For example, every time, and these associations are formed from experience. So every time you see lightning, a little while later you hear thunder. But then once you have formed the association, then you can make predictions. If you see lightning, you can say, I'm going to hear thunder. If you don't see the lightning, and if you hear thunder, you're going to say, lightning must have struck some place nearby because you formed the association, you make the inference. And so it's actually a very good theory. It turns out pretty much all of machine learning is basically associationism at a mathematical level. So that's how we're actually operating. Conceding that everything is done through associations, here's the biggest problem. The fundamental problem of how the brain works has not really been answered by saying it's through associations. So we've got to ask, how are these associations stored and how are they used? And that was a question nobody had an answer for till the mid-1800s, where improvements in microscopy basically told everybody that the brain is a network of cells, specialized cells. And it wasn't until the late 1800s that we realized that these specialized cells that these cells are specialized, they're very different, they're neurons. So this was in the 1800s, and here's what we found, that the brain is basically this massive network of neurons. Each neuron has many incoming connections from other neurons, and each neuron connects out to many neurons. That's how the brain is constructed. And the first person to hypothesize that the way the brain works is dependent not merely on the fact that it's connected, but that the information itself is stored in the connections. This was Alexander Bain in the late in the 1870s. In 1873, he wrote this book called The Mind and Body. And he said that the information actually lies in the connections. So Bain was a philosopher, a mathematician, a logician, a linguist, a professor. In those days, if you were an academician, you were a little bit of everything. And so he was one too. And he actually came up with circuit ideas. So he actually drew these examples. So here's one where he showed that the same network can have different outputs depending on the inputs. Here, for example, if you think of all inputs and outputs as Boolean, they either fire or they don't. If A and B fire, X fires. If A and C fire, Z fires. If B and C fire, Y fires. So depending on the input pattern, the same circuit can produce different outputs. And he even had more complex things, like he showed that the output can change based on the level of the input. So here, for example, if the input is weak, then only Y will fire. But if the input is strong, X gets 2 copies of it, and that should be enough to make X fire. So he had these interesting ideas. Now, all of these are very commonplace for us today. But in the 1800s, this was kind of anathema. People thought it didn't make sense. But then here's the key piece. The earliest models of what are recognizably artificial neural networks go back to 1873. So although they're becoming big now, the ideas have been around for 150 years at this point. And Bain also explained, based on this model, how memories might be made. So when 2 impressions concur or closely succeed one another, the nerve currents find some bridge or place of continuity, better or worse, according to the abundance of nerve matter available for the transition. So he basically says that if 2 neurons which are connected, fire together, the connection becomes stronger. He predicts Hebbian learning, the modern theories of computational neural networks, and this was in 1873. Now, in 1873, the rest of the world was not so smart. And so he postulated that everybody disagreed with him. They thought he was crazy. He faced a lot of opposition. And he postulated that there must be 1 million neurons and 5 billion connections to acquire 200,000 percepts. Then, in the face of so much opposition, in 1883, he came to the realization that 200,000 acquisitions are completed acquisitions, but there's a process of learning, during which you're going to be storing a lot of partially formed relationships. And so you will need a lot more connections than that. And he figured that the brain was simply not large enough to store all of this information. And by the time he died, 1903, he agreed with all of his critics. He apologized for his fraudulent theories and recanted. Well, he was right the first time around. He was wrong when he recanted. The brain is large enough to store everything that you can think of. The brain has 18 billion neurons and 100 trillion connections. And so the brain is indeed connectionist. It's a connectionist machine. Neurons connect to other neurons, and the processing capacity of the brain is a function of the connections. It's all about how the neurons are connected to one another. The individual units are themselves very simple. Just by connecting these very simple units in complicated ways, you can make it do all kinds of magical things. And so modern connectionist machines emulate this architecture. They are composed of a network of processing elements where the individual elements are very simple, and the actual capacity, the computational magic that they perform, lies in the manner in which these very simple units are connected. And so this is fundamentally different from the standard laptop, computers that you've got, your laptops, your phones, and so on. Those of you who are electrical engineers know that your phone or your laptop uses something called the von Neumann or Harvard architecture. So what happens here is that you have a processor, and then you have a separate memory, and programs and data are stored in the memory. The difference between von Neumann and Harvard architectures is whether the programs and data have different portions of memory, or they can be in the same region. But the nice thing with the structure is that the processing is separate. So if you want the machine to do something different, all you have to do is to change whatever is in the memory, and the machine is going to do something different, which is why this tiny little machine that you've got, the phone, it can perform so many different things because all you do is load a different thing into memory. It's very flexible. It's very versatile. On the other hand, connectionist machines like neural networks are very different in structure. Here, there's no separation between memory and the processor. The entire machine is the program, because the manner in which the units are connected is what defines the program. If you want to change the program, you have to change the entire machine, which is why you don't actually construct neural networks, you emulate neural networks on von Neumann architectures. And so, to recap, neural network-based AI has taken over most AI tasks that originally began as computational models of the brain, or more generally as models of cognition. The earliest model of cognition was associationism. The more recent model is connectionist, which says neurons connect to neurons, and the workings of the brain are encoded in these connections. And current neural network models are connectionist machines. So, having established that, here's what we've come to, here's where we're at. We want the brain as a connectionist machine. So to be able to emulate it, we want connectionist machines. These are networks of processing elements where all the world knowledge, the elements themselves are simple, all the world knowledge is stored in the connections between the elements. So, but before that, we need to actually model the units, right? Connections are simple, it's just a line between two units. So there must be some magic in the units. What do these units look like? For that, we're going to go back to the brain and the individual units in the brain, which are the neurons. So that's what the standard neuron looks like. It's got a head, which we call the soma, many connections, these are tendrils going out through which incoming signals come into the neuron. And when the total incoming signal exceeds some threshold, the neuron fires, and that signal goes out with the long leg called the axon to downstream neurons. And the axon is protected by this sheet of fat called the myelin sheet. And it turns out, that it's the key portion of your brain. If you get rid of the fat that protects the axon, your brain is going to fall apart. And in fact, people have found that the difference between really smart people and not so smart people, it doesn't depend on the number of neurons in the head, it depends on the number of amount of myelin. So the more fat you have in your head, the smarter you are. Being a fat head is actually a compliment. Anyway, so this is what the neuron looks like, right? Now, so how do we model this? Wait a minute, where did I go? This is so annoying, sorry. Somewhere here. So the first people to actually try to come up with a computational model for a neuron were these two guys, Warren McCulloch and Walter Pitts. Now McCulloch was a professor in the University of Chicago at the time, a very well-known physicist, and Pitts was a homeless guy who basically went and knocked on McCulloch's door and asked for a place to stay in exchange for doing math. So believe it or not, the guy on the right is not the homeless guy, he's McCulloch, and the guy on the left is Pitts. And so Pitts was a special person. He actually never went to school. He would spend his spare time, he ran away from home, he would spend his spare time corresponding with people like Bertrand Russell, and then eventually ended up in McCulloch's home. They worked on the first model of the neuron, called the McCulloch-Pitts model. And eventually Walter Pitts became a professor in MIT. And when McCulloch died, Pitts died shortly thereafter because he was so emotionally dependent on McCulloch. Anyway, the model that they came up with is what we're all kind of partially familiar with as the perceptron. And when they came up with this model, Pitts was only 20 years old, really young. He, at the age of 20, he created the model that's the basis of everything that we're using in AI today. So here's what the model was. It's a very simple computational model. Each neuron has a bunch of connections and a bunch of inputs. Each input has some weight. And so if the total weighted sum of all of the inputs to the neuron exceeds a threshold, the neuron fires. That's it. But there was a little more to it than that. They said that these connections, which they call synapses, based on the biology of the neuron itself, can be of two kinds, excitatory synapses and inhibitory synapses. And any signal from an inhibitory synapse will just shut the neuron down and force the output to zero. Excitatory synapses bring in signals that can make the neuron fire. And so based on that, they showed that this unit can model any Boolean gate, for instance. So in every case, these are some examples that they have from their paper. In every case, the neuron to the extreme right, that is the neuron whose operation is being analyzed, that will fire if it gets at least two inputs. Now you can see that the figure on the top left, if neuron 1 fires, 1 unit of time later, neuron 2 gets 2 inputs and it will fire. So it's just a simple delay. The top right, if either 1 or 2 fire, the neuron 3 is going to get 2 inputs and it will fire. So that's 1 or 2. It's the Boolean operation of or. The one to the bottom left, both 1 and 2 will have to fire for neuron 3 to get 2 inputs. So it's the Boolean operation and, it's 1 and 2. Now, the one to the bottom right, if 1 fires, neuron 3 will fire unless if 2 fires, and 2 has an inhibitory connection. So this is 1 and not 2. That's the Boolean operation being modeled by this neuron. So once you can compose gates of this kind, you can compose pretty much any Boolean circuit. And so they basically came up with this model which said it can model any Boolean circuit, but then they have too many claims. They claim their machine could emulate a Turing machine, which cannot because it's a finite state machine. And they said you can do these things, but they didn't provide a mechanism whereby the network actually learns to do things, whereas the brain, as we know, is a learning machine. So for learning, we have to wait for this guy, Donald Hebb, who wrote this book called This Organization of Behavior in 1949. Now, Hebb was another very interesting guy. All of these old scientists were interesting. At some point, he actually wanted to be a hobo. And then he did everything from farm work to whatever you name it. And then suddenly decided that he wanted to do something serious. So he gave up all of his fun existence and went off to become a neurophysician at Harvard. And this was the book he wrote as part of his research. He came up with this concept which said neurons that fire together, wire together. So what is that? Now, the way the neurons work, at the synaptic connection, there's no actual physical connection. You have the synaptic knob, and then you have the other neuron that it's trying to signal to. And anytime this neuron wants to signal to this one, it's going to emit some chemicals which transmit signals to the second neuron. Now, what happens is that anytime one neuron actually excites the second one, the head becomes a little bigger. So the next time it is more capable of exciting the second neuron. So mathematically speaking, if both the first and the second neuron fire, the connection becomes stronger. So if you think of this as a weight to the connection, then you can say that the weight of any connection is going to increase by some small value eta if both the input and output are simultaneously 1. So this is the Hebbian learning rule. It's called, Hebb stated it as neurons that fire together, wire together. Now, we still use it. Hebbian learning is used everywhere these days, but it had a fundamental problem. And the fundamental problem is that the weight is only allowed to increase. There's basically, although Hebb came up with improved models later, the basic model has no way for the weights to decrease. So if you wait for long enough, all the weights are going to saturate and the entire machine is going to become a useless machine. It's not computing anything specific. So the next improvement actually came from this guy, Rosenblatt. He was a professor over in Yale, and he invented the solution to everything, also known as the perceptron. This was in 1958. Now, his perceptron was a complicated, it was actually a 3-layer network. And it could compute pretty much any Boolean function if it got large enough, but it had to be, arbitrarily large to compute any Boolean function. But the basic idea, the individual units in his model comprised something like this. A neuron would get lots of inputs. Each input would have its own weight. And if the weighted sum of all the inputs exceeded a threshold, it would fire. If it didn't exceed the threshold, it would not fire. So this was a simple perceptron. And his perceptron, now again, there's a lot of, I just discovered, in fact, Jim Baker discovered for us recently that there's a great deal of misinformation about Frank Rosenblatt's work on the web, including in Wikipedia, which goes to prove that Wikipedia is not really to be trusted. So everybody will tell you that Rosenblatt's model was very naive. That's not the case. But here is his model was a very simple one hidden layer network. And here's what he sold it as, and here's what everybody thought was true. It is the embryo of an electronic computer that the Navy expects will be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. This is what was claimed in 1958. Or Frankenstein monster designed by the Navy that thinks. This was also in 1958. So there was a lot of hype about this model. And what Rosenblatt did, which was an improvement over the McCulloch-Pitts model, is that he also gave us a learning mechanism. So the way he said it, if the perceptron is currently producing some output and the output is wrong, then you change the weight in proportion to the error. between what you want the perceptron to output and what it actually outputs. So, and he showed that this learning rule is convergent, and if the classes, if you're trying to perform a classification task, and if the classes are linearly separable, then this unit can actually learn to separate the classes. So it was a very significant contribution, which set the basis for everything that we do today. Now, here's what, again, this perceptron can very easily model pretty much all the gates. So on the left, in all of these figures, there's a number inside the circle, that's the threshold. There's a number on top of each line, that's the weight of the line. I'm assuming all inputs and outputs are Boolean. So if the weighted sum of the inputs matches or exceeds the threshold, the neuron will fire. And you can see that on the top left, and only if both x and y are 1 is the total input equal to the threshold. So that's x and y. And the bottom, if the threshold is 1, so if either x or y are 1, then the input is going to match the threshold. So this is x or y. On the right, if x is 1, then the input is -1 because the weight is -1. And so the neuron will not fire. Whereas if x is 0, the input is 0, which matches the threshold, and the neuron will fire. So it's actually a negation, not x. And of course, once you can model any Boolean gate, you can actually model, it gets pretty complicated, right? You can, but then there was a misconception for a while that a circuit such as a unit such as this could perhaps model the XOR. Now, this was not Frank Rosenblatt's misconception, as I found, but this is a general misconception by others. And so there is no way you can actually set this unit to perform the XOR. And we'll see why in a bit. Now, so what this means is that a single neuron is not enough, obviously, right? But if you look at the brain is not just a neuron. The brain is actually a connection of neurons. So individual neurons, the elements are weak computational elements. You need to network them to get greater capacity. This is so, let's go back and look at this. I can actually connect up 3 of these perceptrons, and now I can compute the XOR. So the upper unit produces X or Y, this lower one is not X or not Y, and then the output ANDs the 2 outputs. The final neuron ANDs the outputs of the 2 intermediate neurons. And now this little triplet of neurons, this network, can compute the XOR. Now, a little bit of terminology. The output of the guys in the first layer, you don't really need to know what it is, right? So we will call these the hidden layer, because although you could see their output, you don't need to know what their individual outputs are. You're only interested in the final output of the third neuron. So that's the output neuron. Anyway, once you realize that you can begin connecting these guys up to compose Boolean circuits, then you realize you can compute pretty much any Boolean circuit, right? So I can get this really horrible, ugly function on top. I can construct a multi-layer perceptron for it. Basically, take a bunch of perceptrons, connect them up, and I have a network of perceptrons which will give me this crazy function. So here's where we are at this point. What we know is that neural networks, which began as computational models of the brain, are connectionist machines, which comprise networks of neural units. The McCulloch-Pitts model modeled the neurons as Boolean threshold units, but they had no learning rule. Hebb came up with a learning rule for the neurons that fire together or wire together, but it's unstable because if you wait long enough, all of the connections weights will saturate. And then you have Rosenblatt's perceptron, which is a variant of the McCulloch-Pitts neuron with a provably convergent learning rule. But the individual units are limited in their capacity. You need multiple layers to model arbitrarily complex Boolean functions. So all very good, right? I'm talking about Boolean stuff. But our brain is not Boolean. I'm not working on binary inputs and I'm not producing binary outputs. So how do we make the deal? So let's first consider the case where the inputs are real value, but we're still making Boolean predictions, right? And which is classification, for instance, is a large part of what we do, and that's a Boolean operation. So for this, let's go back and look at the basic perceptron itself. Again, you have a perceptron has a collection of inputs. Each input has an associated weight. If the weighted sum of the inputs and the inputs can now be real valued, the weights can be real valued. If the weighted sum of the inputs matches the threshold, the neuron will fire, otherwise it will not fire. So this now you can also make a minor modification. You can say that you're computing a weighted sum, an affine function of the inputs, and you're passing it to a threshold function. Meaning if the affine function is non-negative, then the neuron will fire. The threshold function will output a 1, otherwise it will output a 0. And then once you write it that way, you can replace the threshold function with other functions, like a sigmoid. But anyway, let's go back to this business of just using the threshold. So what does it look like? I have a weighted sum of inputs, and if this weighted sum of input matches a threshold or exceeds it, the output will be 1. On the other side, the output will be 0. So the boundary between these two is where the weighted sum of inputs exactly matches the threshold. That is the equation for a hyperplane, right? Summation Wi xi equals constant is the equation for a hyperplane. So the way it works, there is a hyperplane in the space. On one side of the hyperplane, the output is going to be a 1. On the other side, the output is going to be a 0. So this is just a simple linear classifier. And if you actually plotted this function, say in 2 dimensions, then the function is going to look like this Heaviside function where there's a linear boundary. On one side, the output is 0, the other side, the output is 1. And now you can see why a perceptron can perform Boolean operations. So when I'm working on Boolean inputs, the inputs are either 0 or 1. So if I have 2 Boolean inputs, the input combinations are either 0, 0, 0, 1, 1, 0, or 1, 1. Now I can have a perceptron with a boundary shown on the left side, and you can see that the output is going to be 1 for the combination 0, 1, 1, 1, and 1, 0. That's an OR gate. Whereas if I shift the same boundary to this guy on the right hand side, that's an AND gate because it's only going to output a 1 when the input combination is 1, 1, right? If I shift it to the figure or to the extreme right, you can see that it's an OR gate, right? It's ignoring one input, it's going to flip the other one. And right here, you can also see why you cannot do an XOR with a perceptron. And the reason you cannot do an XOR is that for an XOR, the output is 1 along the diagonal and 0 along the other diagonal. So the output will have to go up and then come back down. But a perceptron only goes up, right? So you cannot, obviously, you cannot do an XOR with a perceptron. Now, if once I know how to do something of this kind, wait a minute. This is so annoying. So there you go. Okay. So once I know how to construct a step function, and I know that I can connect up perceptrons, I can do a lot of really magical things. So let's say I want to build a little MLP, a network of perceptrons. We're calling it a multi-layer perceptron, which produces this decision boundary. I want a 1 when the input is inside the pentagon, a 0 when it's outside. All of you can immediately tell me how to compose this, right? Here's what I would do. I'm going to have one perceptron which captures the lower boundary. The output will be 1 above it, 0 below it. Another one for the second boundary. The output is going to be 1 on this side, 0 on the other side. The third one for this boundary. The fourth one for this one. The fifth one for this one, right? And now the final output is going to be a perceptron which just adds the all 5 outputs. All 5 have to be 1. And all 5 are 1 only inside the pentagon. At least one of them is 0 outside. And so this little network is going to give me a pentagonal decision boundary, right? So beautiful. How about constructing a decision boundary of this kind? This is easy. I know how to construct an individual pentagon. So I can now have one subnetwork which constructs the first pentagon, another subnetwork which constructs the second pentagon. I can have a final output which ORs the 2. I have my double pentagon, right? So how about these decision boundaries? these crazy looking things, like something like shaped like the figure to the left, or something shown like the somewhat humanoid figure in the middle, or maybe a decision boundary in the shape of a horse. How would you do it? Well, I'll leave it to you guys to decide how for a bit. But then now, once you realize, you can construct any decision boundary, it becomes apparent how we can perform pretty complex classification tasks. For example, let's say I want to build a network which is just recognizing the digit 2. And my input is an image. It's going to be hundreds or thousands of pixels, right? But in this high dimensional space, the region of the space which represents the digit 2 is going to be some closed region. And so all I need to do is to construct an MLP that captures that decision region, the one that I've shown using the peanut in this figure. And the same concept that I just showed you earlier extends, right? So the story so far, we've just added MLPs can model Boolean functions, individual perceptrons can act as Boolean weights, and networks of perceptrons are Boolean functions. But they're Boolean machines. They represent Boolean functions over linear boundaries. They can represent arbitrary decision boundaries, and they can be used to classify data as a result, right? We can say everything that's a 2 will lie inside this closed region. I can model that decision boundary. So we saw what they can do, right? Now, is there some kind of a semantic interpretation for what the perceptrons actually do, the individual perceptrons and what the network does, and the network? So let's go back and look at the perceptron again. Now, the perceptron is looking at a weighted sum of inputs. If it exceeds a threshold, it's going to fire, otherwise it doesn't fire, right? Now, what do these weights tell us? Now, if I want to write this in algebraic terms, the weight is a vector, which is the same size as the input. The input is a vector. So the weighted sum of inputs is just the inner product between the weights vector and the input vector, right? If the inner product exceeds a threshold, the perceptron is going to fire. Now, here's a strange fact. In high dimensional space, all vectors are approximately the same length. That's because if you take any particular, a sphere of any size in high dimensional space, as the dimensionality of the space increases, the majority of the volume, which can go up to 99.99999% of the volume, is going to be within a fraction of a very thin scale region around the surface of the sphere itself, right? This is a well-known fact. Which means that if I go up to 1,000 dimensions, if I take a random vector, any 2 random vectors are going to be more or less the same length. You may not have thought hard about it, but this is true. So here, if I'm looking at the weights, the inner product of the two weights, the weights and the input, that's basically just the length of the weight times the length of the input times the cosine between the two, right? The length itself, as we saw, is irrelevant. They're all the same length. So what this means is that the perceptron will fire if the cosine is small enough, large enough, or if the angle between the two is small enough. So the weight represents a standard direction in the space. Your input is some other vector, and the closer the input is in angle to the weights, the greater the inner product between the two. And so if the input has a small enough angle with respect to the weight, then the perceptron will fire, otherwise it won't. So basically your track is going to fire if the input lies within a small cone of the weights vector. Now here's the consequence of it. What does this mean? You're really saying that you're looking at the correlation between the weight vector and the input. And if the correlation exceeds the threshold, it's going to fire, right? So what this means is that if I'm looking for a specific pattern, I can blindly set my weights vector to be that pattern. For example, if I'm trying to construct a perceptron which recognizes the digit 2 in grids, all I will do is to set my weights vector to be the digit 2. Now, anytime you give it an input, it's just computing the correlation between the two. the weights and the input. And if the correlation is small, it won't fire. If the correlation exceeds some threshold, we could set it to some 0.8 in this case, it's going to fire, right? Easy enough. So the weights represent the pattern for the individual perceptrons. The weights represent the pattern that the perceptron is looking for, which is interesting, right? And so, what is the perceptron, multi-layer perceptron as a Boolean function? Well, you can think of all of the perceptrons in the first layer, in the first layer, as feature detectors, where the weights of the perceptron tell you what feature it is looking for, right? And the subsequent perceptron layers are actually sort of looking if certain combinations of features have happened in the input. So what this means is that the first layer, it's very important for the first layer to capture these features, because if it doesn't, you're not getting the basic features that you need to actually recognize the input. And so if I were doing something like, trying to see if this grid of picks of LEDs is composing a valid digit, then I would expect that the first layer of perceptrons would all capture different components of digits. And the next layer would actually put these components together and be trying to detect individual digits. And the final one is going to OR the two. This would be a perfectly reasonable thing to do. And again, here is a network that you could handcraft for this task, right? If someone were to ask you to handcraft it, this is basically what you do, and it would just work. So, going over, MLPs we saw are basically Boolean patterns. So the new lesson over here is that I can think of this MLP as a Boolean pattern detector. The first level neurons detect features, and the rest of the network basically say, have this combination of features happen? Has this combination of features happen? It's answering Boolean questions over the outputs of the basic pattern detectors itself. And so the rest of the network can be thought of as a Boolean function, right? And so MLPs can be thought of as Boolean pattern detectors over patterns detected by individual perceptrons. And so as an extra, you can use it for classification. The network will fire if the combination of the detected basic features matches an acceptable pattern for the desired class of signal. For example, if I'm trying to do a face recognizer, then have I detected a nose, an eye, a mouth, something like that. But then all of this, we're still speaking of Boolean outputs, right? We started off saying, let's look at Boolean inputs and Boolean outputs. Then I took the next step and said, let's look at real valued inputs and classification Boolean outputs. But can I do continuous valued outputs? So let's look at that. How can MLPs perform continuous valued regression? For this, let me start off by trying to model a simple scalar function. F of x. X is a scalar, f of x is also a scalar, right? But for that, the first thing I will do is to construct this little circuit. It has two threshold gates. The first one on top fires if the input exceeds the threshold T1. The second one fires if the input exceeds the threshold T2. I'm going to be adding their outputs with weight 1 and -1 respectively. So what happens? So the input is less than T1, neither of them is fired. So the output is 0. When the input is greater than T1 and less than T2, the first one fires and the second one doesn't fire. So the sum of their outputs is going to be +1. When the input exceeds T2, both of them fire, their outputs cancel out, and the total output becomes 0. So the output is there's a 1 between T1 and T2, and it's 0 elsewhere, right? That's all I need to do. Now, if I want to model this really funky function shown by the blue curve, I can take the entire range, slice it up into little block regions. I can construct one subnet to compose a little pulse within that region. I can scale the output of the weight, which is the height of the function in that region, and then add them all up, right? And this little network is going to give you the stepwise approximation to the blue curve. I can make the approximation arbitrarily precise by making the individual bands narrower. And so what this means is that an NLP with many units can model an arbitrary function of an input to arbitrary precision. So, and this generalizes to functions of any number of inputs, not just scalar inputs. We'll see how in a bit. And so, to conclude this part, MLPs can also model continuous value functions. That's what we just seen. I'll pause here for a minute. Do we have any questions? Oh, okay. Either I'm brilliantly clear or anyways. So as a recap, right? If I think of the perceptron as a basic threshold unit, it's a gate which fires if the weighted sum of inputs exceeds the threshold, or I can say the weighted sum of inputs plus a bias, which is basically an affine function of the inputs, is going to fire if the affine function of the inputs is positive. It's not going to fire if this affine function of inputs is not positive, negative, right? And so I can rewrite it as saying I first compute an affine function of the input C. I put it through a threshold activation, which outputs a 1 if Z is non-negative and 0 if Z is negative, right? And so once I write it that way, I can replace this threshold function with a smoother version of the threshold function, like a sigmoid or other. And so you can think of it as first computing an affine function of the inputs and then putting it through an activation function. And the activation can be pretty much anything. And so the activations don't have to be sigmoids. They can be, tanages, reviews, all the other things that you're familiar with. But for the purpose of explanation, it's useful to think of, continue to look at threshold activations because they make it very easy to develop the intuitions. So here's what an MLP looks like. It's a network of neurons and it's generally layered, right? So we keep talking about deep neural networks. What do we mean by deep neural networks? Now, intuitively that deep neural networks have something to do with having too many layers. What's a layer? How do you define a layer, right? We have to answer these questions. These are not abstract concepts where everything falls in a line. It's a layer. That's not what it is, right? There's a mathematical definition for all of these things. So here's how you define deep. Now, suppose I draw a graph, a directed graph. Now, a directed graph is going to have a source. It's going to have a sink. One or more sources, one or more sinks, right? And so there are paths between source and sink. The depth of the graph is the length of the longest path from source to sink. So over here, I have a path that is length 1. I also have a path that is length 2. The depth of this graph is 2. Over here, I have a path which is length 1, a path which is length 2, and a path which is length 3. The depth of this graph is 3. So you get the idea of what it means for a graph to be deep, right? Now, a neural network is basically a graph. It's got a bunch of inputs, and then the inputs are going to get processed by one set of neurons. Their outputs are going to be processed by another set of neurons. Their outputs are going to be processed by another set of neurons, and so on. It's a graph. The source is the input. The sink is the final node at your input. And so the depth of the network is the length of the longest path from input to output. So here, for example, the depth of this network is 1, 2, 3. The gray circles represent inputs. Here, the figure in the top, the depth of that network is 2. If you look at the figure in the middle, with the yellow, red, blue, and gray boxes, there are paths from the input to the output that are only 2, 3, and 4 long, but the depth of the network itself is 4, because the 4 is the longest path. Now, what do we mean by a layer? A layer is a set of neurons that have the same depth with respect to the input. So in this figure, all of the red neurons have a depth of 1 with respect to the input. So the red neurons form the first layer. Here, all of the green neurons have a depth of 2 with respect to the inputs. So the green neurons form the second layer. The yellow neurons form the third layer. And the blue neurons form the fourth layer, right? Now observe again that there's a path which is only length 3 to the blue, but the longest path is length 4, right? So all of the blue neurons have a depth of 4, they form the fourth layer. So regardless of how I draw it, visually you would think that these 4 neurons form the second layer. They don't, right? Some of them actually belong to the first layer. So there's a very formal definition for what a layer is. Now an MLP can have real or Boolean stimuli. The outputs can be real or Boolean values, we saw. It doesn't have to have just a single output, it can have multiple outputs. What can the network compute? We've got some idea of what it can compute, right? But then, can we get a better idea of what input-output relationships it can model and what are the restrictions? So we've seen that an MLP can model pretty much any Boolean function if you construct it properly, right? We also saw that it can model any continuous valued function if you model it, construct it properly. But what are the limitations? So first, let's look at Boolean functions. How well do they model Boolean functions? We've already seen that individual perceptrons can model Boolean gates, right? This is easy. We've also seen, but then individual model perceptrons can model some pretty complicated things, not just simple Boolean gates. Here's, for example, what I will call a universal AND gate. A universal AND gate, this one is going to fire if any of the if all of the first L inputs are all 1 and the remaining L inputs are all 0. Any other combination and it will not fire. Now, why is that? You can see. Suppose I set the first L inputs to 1 and the remaining inputs to 0, then the total input is L, right? Because from L onwards, all the inputs are 0. Now, if any of the first L inputs flips from being 0 to being 1 to 0, the total input is going to be less than L. It won't match the threshold and it won't fire, right? Similarly, if any of these remaining inputs from L plus 1 become a 1, because their weights are -1, they're going to subtract something from the total input. So the total input is going to be less than L and it won't fire. So this thing is only going to fire if the first L inputs are 1 and the remaining inputs are 0. So there's a very specific combination under which it can fire. Or here is the counterpart. This is going to fire if any of the first L are 1 or if any of the remaining inputs are 0. So again, you can see how this works. The only condition under which it doesn't fire is if all of the first L inputs are 0 and all of the remaining inputs are 1, right? So in that case, they're going to be, you can see that if all of the first L inputs are 0 and all of the remaining inputs are 1, the total input is going to be L minus N, because there are there are L inputs that are supposed to be 1 and N minus L inputs which are going to be 0, but their weights are minus 1, so we flip it. And so if the threshold is 1 more than this, L minus N plus 1 is going to fire if any of the first L are 1 or if any of the remaining are 0, right? So this is that's a universal OR gate. Or here's something else that you can never do with a Boolean gate, the majority gate. So this one is going to fire if at least k of the inputs are 1. And if k is greater than n over 2, then it's going to fire if the majority of inputs are 1. Now to construct this operation using simple Boolean gates, you need an exponentially large circuit, exponential in the number of inputs. But you can do this using a single threshold gate. So perceptrons are much more powerful than simple Boolean gates, as you can see. In spite of all this magical ability, they can't model an XOR, right? For an XOR, we saw we need a multi-layer perceptron. So although they're very powerful, they can't do everything. So once you do that, we know that they can also model much more complicated Boolean circuits, right? So a multilayer perceptron can, the key word being can, model any Boolean function. In other words, a multilayer perceptron is a universal Boolean function. You give me a Boolean function, I can compose an MLP that will compute it. It's a universal Boolean function. But then, here's the thing. If I look at this crazy circuit to the left, it has 1, 2, 3 layers, right? The depth of the circuit is 3. So, how many layers do I need? I mean, can we think of constructing that Boolean function using fewer than 3 layers? How many layers will I need to construct a Boolean function, or this particular Boolean function? You'd like to answer that question, right? So, is there any restriction on the number of layers in order to construct any Boolean function? To answer this question, let's go back and look at what a Boolean function is. A Boolean function is just a truth table, right? I give you the inputs, I give you the output. I just have to list out the patterns of inputs for which the output is 1. I don't need to list out the remaining, right? For the rest of them, the output is implicitly 0. And so now, a Boolean, this truth table is a Boolean function. So anytime I get an input, I got to check if any of these patterns match. If a pattern matches, the output is 1, otherwise the output is 0, right? So I can write this as in this manner. So for each row of the table, I can write this as a DNF formula, which is basically the sum of products formed. And so for each row, I'm going to get one of these clauses in the formula. The first clause, for example, over here, says not x1, not x2, x3, x4, not x5, which means this is going to be a 1 if x1 is 0, x2 is 0, x3 is 1, x4 is 1, and x5 is 0. That's the first row, right? Similarly, I have the second one which says not x1, x2, not x3, x4, x5, right? Or the third one says not x1, x2, x3, not x4, not x5. So I can actually write out one clause for every row, and then just sum the outputs, and I'm going to have my Boolean function, right? Any Boolean function can be written in this manner, because every Boolean function is eventually just a truth table. I'm just explicitly listing out all the combinations for which the output is 1. And now I can compose an MLP for it, right? I'm going to have one, remember, perceptrons are universal AND gates, right? So I can compose one perceptron for the first guy, one for the second, one for the third clause, one for the fourth, one for the fifth, one for the sixth. One perceptron or all their outputs. And so using just a single hidden layer, I can construct an MLP that computes this Boolean function. This is something that Rosenblatt realized way back in the 50s, in fact. A single hidden layer multilayer perceptron is a universal Boolean function. You give me a Boolean function, I can compose an MLP with just one hidden layer which computes it. But then if I do this, right, how large does the network get? To understand how large the network gets, let's take a look at the truth table in a different manner. How many of you are familiar with Carnot maps? A very small number, right? So a Carnot map is a topological way of representing input patterns. So here, for example, I have 4 inputs, W, X, Y, and Z. So the 4 rows represent the 4 combinations of W and X. The 4 columns represent the 4 combinations of Y and Z. And what you'll observe is that if you look at any 2 adjacent rows, they differ in only 1 bit. And the top row and the bottom row also differ in only 1 bit. Similarly, any 2 adjacent columns differ in only 1 bit. So if you think of this whole thing as a torus, where this right edge connects to the left edge, the top edge connects to the bottom edge, it's a topologically accurate way of representing all 16 combinations. Where if you take one step into an adjacent cell, only 1 bit changes at each time. And now in this thing, I can just, so these 16 boxes represent the 16 combinations of the inputs. I can highlight those boxes where the output is 1, right? There are 7 combinations where the output is 1. So if I just did a simple DNF formula, a naive DNF formula, I'm going to get 7 clauses in my input. And so a simple MLP, which simply implements this function is going to have 7 neurons in the hidden layer and an output neuron, right? But then here's what I can do. I can group things, right? If you look at the 4 things in the first column, it says that regardless of the values of W and X, the output is 1, then YZ is 0, 0, right? So I can group those guys because they're neighboring and just collapse those 4 units into a single clause which says not Y, not Z, right? Similarly, I can group these 2 things in green, and which basically say that so long as WX and WX form the pattern 0, 1, and so long as Y is 0, the value of Z doesn't matter, right? And so I can group those, and that's going to give me the clause not W, X, not Y. And so by grouping neighboring things together, I can reduce the total number of clauses to a very small number of clauses. That is the size of the formula, smallest BNF formula for this particular Boolean function. And so if I group it, this one hidden layer network is going to need only 3 neurons in the hidden layer, right? But then what is the worst case? The worst case is, so this is what it's going to look like, right? What is the worst case? The worst case, what is the largest irreducible BNF? Anyone? Something like this, right? So alternative. You can't group anything. So if I have n inputs, I'm going to have 2 raised to n boxes. So it's going to be 2 raised to n minus 1 highlighted boxes. And 2 raised to n minus 1 highlighted boxes simply cannot be reduced. So this circuit is going to require 8 neurons in the hidden layer and an output, right? Now, this is with only 4 inputs. If I go up to 6 inputs, here's the 6 input version of the Carnot map. It's a cuboid. It's a hypercuboid, right? And here, I'm going to have 32 alternating clauses which are 1. And so if I want to do a 1 hidden layer network, this is going to require 32 neurons in the hidden layer and 1 output, right? So in general, what will happen is that if I have n inputs, then the worst case, if I'm trying to do this XOR, if I'm going to be emulating Boolean gates, and if I want to build a circuit with just 1 hidden layer, that 1 hidden layer circuit is going to need 2 raised to n minus 1 neurons in the worst case, right? That's large because your typical, I mean, you rarely ever deal with 4-dimensional inputs. You're dealing with 4,000 dimensional inputs. It's going to be 2 raised to 3,999. It's not going to be a very small circuit if you're just doing this with 1 hidden layer. But then let's look at the problem again, right? If I want to use multiple hidden layers, then what happens? Here's the actual function that we're trying to model in these 2 cases. These are XORs. So the first one is W XOR X, XOR Y, XOR Z, right? The second one is an XOR of 6 units. And we know that a single XOR can be modeled using 3 neurons in 2 layers, right? So this is an XOR, right? We've already seen this. That means I can construct this network like so. I can have 3 neurons for the first XOR, XOR its output with the next one, which is 3 neurons, XOR that output with the next one, which is 3 neurons, and so on. So the first one is going to require 3 sets of XORs, 9 neurons, or this one is going to require 5 sets of XORs, which is 15 neurons, right? Very small. So what happens is that in general, for every new variable, I'm just adding 3 neurons. In fact, I can do it with 2. So here is the situation that we had when we were trying to do this with 1 hidden layer. You needed 2 raised to n or 2 raised to n neurons in the hidden layer. If you're allowing it to be deep, then you needed 3 times n, order of n. So it went from being exponential in size to being linear in size, just by letting the network be D. But there's something special hidden over here. So I'll take a pause. Can anyone tell me what is the hidden caveat over here? So I'll let you know. Pardon me? That is a different thing, right? So here is the thing. The depth, what is the depth over here? Let's take a look. The depth is a function of the number of inputs. For this to be a small network, let's see how this works, right? You're right about the parallelization. I can always write the XOR, XORs are associative. I can group things in any way. And so instead of just having a network of this kind, where every time I add a new variable, I keep adding 3 neurons on top, I can compute XORs of pairs of inputs. Then I can compute XORs of pairs of those outputs and compute XORs of pairs of those outputs. This network, how deep is it going to be? It's going to be log of n, or 2 times log of n in depth, right? And so if I can arrange the network of depth 2 times log of n, or order log of n, then the number of neurons I require is going to be order n. And here's what happens, right? If I say that the depth of the network is less than 2 times log of n, suppose I fix the depth. Suppose I say I want a depth of 10, that's it, right? If I want a depth of 10, what happens? Even in the structure, after 8 layers, you've reduced the number of inputs by a factor of 2 raised to 416, right? But then after that, you have a gigantic XOR over 10, n over 6, n by 16 inputs, and you have only one more hidden layer, and that hidden layer has to be exponential in the size of the input. So the only way this works is that the depth of the network is actually monotonically related to the size of the input. As the dimensionality of the input increases, the depth of the network has to increase. When that happens, then you can actually model the circuit with the function using a linear number of units. But anytime you have a fixed depth network, then there's an input dimensionality beyond which the size of the circuit will have to become exponential for it to accurately model the function. So a network with fewer than the number of neurons, the number of layers is going to be exponential in size. And if you decide I'm not going to make it exponential in size, then it won't model the function at all. It's going to be erroneous. And in the case of an XOR, missing 1 bit is going to give you 50% error, which basically says, you have 1 neuron less in your circuit. You might as well throw your circuit out and flip a coin. It saves you a lot of trouble, right? So the deep Boolean NLPs that scale linearly with the number of inputs can become exponentially large if they're using only 1 layer. And then here it gets worse. If I have any function where eventually I can write the function as an XOR over some intermediate variables, from there, if I fix or limit the depth of the circuit, it's going to become, you will need it to be exponentially wide to capture the function properly. So again, the XOR is really a parity problem. Any Boolean circuit of depth D using AND, OR, and NOT gates must have size 2 raised to n over 1 over d. Anyway, this is just the theory of it. I'll skip this. But Shannon has some very nice theorems on it, but I'll restrict myself to the conceptual level at this point. So anyway, here's what we've got. An NLP is a universal Boolean function. It can represent a given function, but only if it is sufficiently deep. And depth can be traded off for an exponential growth in the width of the network. And the optimal width and depth depend on the number of variables and the complexity of the Boolean function itself. Right? So the optimal depth depends on the number of variables. It's logarithmically related. The minimal depth to model the function accurately is logarithmically related to the size of the input. So here, even a network, multi-layer perceptrons are universal Boolean machines. Even a network with a single hidden layer is a universal Boolean machine, but a single layer network may require an exponentially large number of perceptrons. Deeper networks may require far fewer neurons than shallower networks to express the same function. They could be exponentially smaller provided the depth is a function of the input itself. No fixed size, fixed depth network can be a universal function. So now that was for Boolean functions, right? Now let's look at classification. The NLP we saw is a function that finds complex decision boundaries over the space of pairs, right? And so we saw why, how you can, what a perceptron, individual perceptron does, it just captures a linear decision boundary. And so we can use that to model fairly complex decision boundaries by simply connecting them up. So in this case, what happens is you can construct the network so that all of the neurons produce a 1 in the region that you are interested in. And if you enclose it properly, then you're going to be able to construct a circuit which outputs a 1 only within the target decision region and 0 elsewhere. And so now you can compose more complex decision boundaries like this one, or this, or these, right? And we know how to do this, right? For example, if I want to model this ugly decision boundary, then all I need to do is to sort of split it up into little polytopes, have one subnet for each polytope, and then order, hierarchically order the lot. I'm going to get my decision boundary. So this you can model arbitrarily complex decision boundaries. But then here's what we did. So this is not the same as the Boolean function, right? What happened was the first layer was a feature detector which detected whether which side of a line the input was on, and then we composed a circuit on top of that. So even assuming that I use the same hypothesis that I can compose any Boolean function using only one hidden layer, this is going to, including the feature detectors, I'm going to need 2 hidden layers, right? So question, how would I actually construct a network for these kinds of decision boundaries using only one hidden layer? Or to give you something more concrete, I'll pause for a second. Can you think of how I would construct a network that gives you this double pentagon decision boundary using only one hidden layer? Something like this. Anyone want to guess? Someone. No one has the courage, or leave the call. Anyways, so it's not easy. Obviously, it was a trick question, right? You were wise to not answer. Here's how it goes. Let's look at how I would construct a diamond-shaped decision boundary. A diamond-shaped decision boundary is going to use 4 neurons, 1 for each of the sides. But then, how is this boundary being modeled? Each of these neurons outputs a 1 on the size of the diamond, on the side of the diamond, and 0 elsewhere. So you're summing the 4 outputs, and to get the diamond, you're comparing the sum against the threshold 4, right? So let's look at the sum. What does the sum look like? The sum of these 4 outputs of these 4 neurons has that figure that looks like the figure up there. This is showing it against the 2 inputs, right? And so only within the diamond itself, the sum is 4. Then there are other regions where the sum is 3, other regions where the sum is 2, right? Now, let me extend it to a pentagonal decision boundary. When I do a pentagonal decision boundary, I'm going to need 5 neurons, right? What does the sum look like? The sum looks like the figure to the top right. It's going to be 5 within the pentagon. Then there are regions where it's 4, and there are most of the space, the region with the sum is 3 or 2, right? Or if I take a hexagon, right, then the sum of these guys actually ends up looking like that. It's going to be 6 within the hexagon, and elsewhere it's going to be lesser than 6. It's never actually going to be less than 2. It's actually going to be never, in this case, it's never going to be less than 3. just to be sure, right? I can keep increasing the number of sides. So if I have a heptagon, then the sum is going to be 7 inside the heptagon, and outside it's going to fall off till it goes to about 3, right? It never goes below 3. If I have 16 sides, this is what it looks like. Inside the pentagon, inside the 16-sided one, whatever it is, the sum is 16. As you go outside, it falls off very quickly and it falls up to 8. This is what I get with 64 sides. Inside the central region, the sum is 64. Then it falls up to, how much do you think it falls up to? Anyone? It's going to fall off to 32, right? And so with 1000, it's going to be 1000 inside, and it's going to fall off very quickly to 500. As I keep increasing the number of sides, the sum of the first layer neurons gives you the structure which is going to be n inside the central region, and it falls off very quickly to n over 2 outside. And so in the limit, it's going to have the shape. As n becomes very large, it's going to be a kind of cylindrical. It's going to be n inside this nearly circular region in the middle. And then very quickly, it's going to fall off to n over 2. So you can sort of, and for, if I increase n enough, and if I make the radius small enough, this figure is going to be a perfect cylinder. Tends to a perfect cylinder, right? That's just the sum of the first layer neurons, right? Sum of the outputs of the first layer neurons. And so, if I want a circular decision boundary, here's what I would do, right? I'm going to get a very large number of, I'm going to model it as a polygon with an extremely large number of sides. And so when I sum the outputs of the first layer boundaries, boundary detectors, that sum is going to be n inside the central circular region, almost circular region, n over 2 outside, or I can add this extra bias term, which subtracts out n over 2. And now the sum is going to be n over 2 inside and 0 outside, right? And now all I can do is to say I'm going to sum the outputs of all of these guys. And in this neuron out here, I'm going to apply a threshold of n over 2. It's going to slice it at n over 2, and the decision boundary is going to be a perfect circle. Okay, how did this help us? Here's how it helps us. Now, suppose I want a decision boundary which is 2 disconnected circles. What would I do? I'm going to have one subnet where the output of the subnet is going to be n over 2 inside the circle and 0 outside. I'm going to have another subnet whose output is going to be n over 2 inside a different circle and 0 outside. But here's the crazy thing, right? If these two circles don't intersect, then simply summing the outputs of both circles is going to look like this. It's going to look like 2 distinct cylinders. Because one subnet composed a cylinder, the other subnet composed a disconnected cylinder. So obviously the outputs of the two don't interact. And so if I simply add the 2 sets, I'm going to get 2 cylinders. If I use a final output neuron with a threshold of n over 2, the decision boundary is going to be 2 disconnected circuits, right? And then it's easy. Here's how I would compose my double pentagon. It's going to be, I'm going to fill it up with circles. And by making the circles small enough and having a large enough number of these guys, I can make this decision boundary arbitrarily precise. It's not going to be exact, but it's going to be an approximation where the approximation error is as small as I want it to be, right? And so what we find is that even a one hidden layer NLP can model any decision boundary provided it's big enough. But then how big? It needs in the limit. For complex decision boundaries, it can require, if I have curves in my decision boundary, it's going to require an infinite or n tending to infinity neurons in the hidden layer, right? But then we already know that this guy could have been constructed using just 12 hidden neurons, right? The moment I add to it one extra layer. So going from one hidden layer to do 2 hidden layers took me from an approximation using, n tending to infinity neurons to absolute precision using only 12 neurons. And so once again, here is the depth versus size trade-off. The moment you begin going deep, the network can be made arbitrary. The number of neurons required to model the same boundaries can become extremely small. And so all of these basically, I'll just skip this. This is theory. But then let's try to look at a somewhat different pattern, right? Worst case decision boundaries. So we want to continue to look at threshold activation methods, but the whole thing generalizes to other nets. Let's look at a decision boundary of this kind. I want the output to be 1 inside the yellow regions and 0 in the gray regions, right? Now for this, I know that if I want to model this decision boundary using just one hidden layer, I already know that a one hidden layer network, if I do it naively, the smart ways of doing it, it's going to require effectively infinite neurons in the hidden layer, right? But then let's look at it more carefully. This circuit can be modeled using this network with 2 hidden layers. Why is that? The pattern over here with 56 hidden neurons, that's because that pattern over there is composed of 16 lines. So what I will need is I will need this first layer of 16 neurons to capture these 16 boundaries. And then on the 16 boundaries, I have this checkerboard of yellow regions. So I'm going to need 1 neuron for each of these yellow regions, which is, combines the outputs, just as we did for the pentagons. And then I'm going to need a final output. And so there are 40 of these yellow regions. So I need 40 neurons in the second layer. I'm going to need 16 neurons in the first layer, and then the final output. So this can be done using 57 total neurons, including the output neuron. So, but then, do I really need these many neurons, right? This is just an XOR, once again, which all checkerboards are XORs. And so all I will need is the 16 neurons for the first layer, and then I'm going to need the XORs for all of the subsequent, the rest of the patterns is just going to be an XOR on the outputs of these neurons. And so the XOR, as we saw, this is an XOR with 16 lines, so it's going to need 15 times 3, or in fact 15 times 2, 30 neurons to capture the XOR, plus 16 for the 16 lines. I can do this with 46 neurons if I let this be deep. Now here, for this simple pattern, maybe it doesn't look, the difference between 56 and 46 may seem like nothing. If I go to something more complex of this kind, this is still not a very complex pattern. This is a very simple pattern. It's composed of 64 lines of this kind, right? And so, and it has 544 of these yellow regions. So if I just wanted to do a 2 hidden layer network, this is going to need 609 neurons. But if I do this, if I realize that this is an XOR, I can do this with actually fewer than 200 neurons. And here I'm assuming I need 3 neurons for each XOR. So you can see that when you get this depth versus breadth trade-off, when things become deep, just by making the network deep, you can reduce the number of neurons required by an exponential amount. But again, here is the caveat, right? I call this an XOR. This is an XOR over 64 variables, 64 lines. In a real world problem, you don't know what the basic number of features are. So you really don't know how many basic pattern detectors you need. And once again, the optimal depth is logarithmically related to the number of basic features. If you go below that, your model is going to be an approximation you are going to have error, right? And so that's going to be an issue. So again, the summary is the number of neurons required in a shallow network here is, it's not actually polynomial, which means it can be exponential in the number of basic patterns and exponential in the dimensionality of the input. But if I make the network B, then I can actually require an exponentially smaller number of neurons in my circuit in my network than I would if my network was shallow, right? Again, this is going back to the simple XOR as an intuition, and XOR actually gives you very, very nice intuitions for this sort of thing. Now, going back again to continuous regression, right? Again, that was looking at classification boundaries. What about regression? So I will stop in a couple of minutes, right? So a simple 3-unit NLP, we said, can generate a square pulse over the input, right? And now we saw that we can use this to construct any odd function. How would you do this in higher dimensions? For higher dimensional inputs, you're going to need subnets to compose cylinders. And then if I have, so this would be a cylinder would be n/2 inside the circle with 0 outside, right? And now if I have some crazy function, I can just compose it by filling it up with cylinders and constructing a function of using as an approximation of a large collection of cylinders. Again, I can approximate it to arbitrary precision by having enough neurons. So a single MLP, a single hidden layer MLP can model any regression function, but once again, you can this sort of the number of neurons required will collapse if you are willing to accept depth. Okay, I'll stop right here because it's time for the break. But what we find is a single layer NLP, single hidden layer NLP, not a single NLP, is a universal function approximator, but it can require an infinite or excellent number of neurons to model a function. More generally, deeper networks will require far fewer neurons, can be. And again, the optimal depth of the network is logarithmically related to the complexity of the pattern that you're trying to capture, except the complexity of the pattern. In the case of XOR, it's very easy to quantify. In real life problems, we don't exactly have to quantify this. We'll see a little more of these things in the second. So it's time for a break, but if you have any questions, I can. Okay, everybody. Thank you. That was amazing. Anyway, so I'll pick up here. We have 10 minutes behind time, which means that I'm going to eat up some of your lunch period. Information is food, right? Anyway, here's where we were. We sort of found that shallow networks, even shallow networks, can be universal approximators if they are sufficiently big. By big, I mean have a sufficiently large number of neurons, sufficiently large number of parameters. But then if you make the networks deep, then the number of neurons and the number of parameters you require can be much smaller to model the same function. And in terms of learning, you know that having fewer parameters means you will do a much better job of learning the function accurately. So that is relevant as well. Now, we're going to, so in a information theoretic sense, we say a neural network can represent any function provided it has sufficient capacity. So it should have the requisite number of neurons in the requisite depth in order to be able to model a function. Now, not all architectures can represent any function. So we will see how. Consider this checkerboard pattern to the top. Right? We know that it is formed from 16 lines. Now, suppose I'm using threshold activations and my first layer neurons only have 8 neurons. So if I have only 8 neurons in my first layer, can I compensate for it by having infinite neurons in the second layer, right? Just make it more, try to increase the expressiveness of the network by increasing the size and layer networks in the later layers. And the answer is no, right? If I have fewer than 16 neurons in the first layer, there's nothing I can do if I'm using threshold activations to capture this decision boundary. Why? Imagine that the 16 neurons capture these 8 neurons. Imagine I have only 8 neurons and they capture these 8 boundaries. Then for each of the 8 boundaries, the neuron is simply going to be able to say whether you're to the right of the boundary or the left of the boundary. It cannot tell you more than that. So which means that by the time the information has gone past the first layer, the only information you will have is this. In which of these strips the input lies, you will not have further information. There's no way for you to be able to make additional distinctions to form the entire checkerboard. Or, here maybe you may think I'm exaggerating. I made those 8 lines parallel. Suppose my 8 neurons capture these 8 boundaries. The problem remains the same. But the 8 neurons in the first layer have gated the information, which means that I cannot compensate for it by adding more neurons in subsequent layers. So basically, all the 8 neurons can tell you is which of these boxes the input lies in, but that is insufficient to form this more complex decision boundary, right? Similarly, even if I have all 16 neurons in the first layer, if I have fewer than 40 neurons in the second layer, I'm not going to be able to compose this decision boundary. I'll miss some of these regions. And so what we find is that it's not enough. You can't just compensate for width with depth. Even if you have a deep enough network, every layer has to be sufficiently wide. Otherwise, you cannot actually model the function. So why is that, right? Why will a network with fewer than 16 neurons in the first layer not be able to represent this decision boundary? The network with fewer than 16 neurons in the first layer can only tell you which of these different regions the input is in. But within this region, it cannot tell you whether you're here or here. For any input within any box, the output of the first layer is going to be the same. So which means that you won't be able to make out within this region whether you're in this yellow box or this gray box or this yellow box or this gray box. Your error is 50%, which is basically useless. So missing one neuron in the first layer can end up giving you 50% error on the simple binary classification task. Now, the reason for this in this particular example is that I'm using threshold activations. So threshold activations can tell you whether the input is to the right of a line or to the left of a line. It doesn't tell you how far away you are from the line. So, which means that if I had only 4 neurons over here, the 4 neurons could tell me which of these strips the input lies in, but it won't tell you where you are within the strip. So there is insufficient information for subsequent layers to reconstruct the entire pattern. So this is where we benefit by having graded outputs. So basically, instead of having, for some reason my slides have changed. Okay, so that's because when I'm using threshold activations, I'm only telling you whether I'm to the right of a line or to the left. I'm not telling you how far away I am from the line, right? From the boundary. Now, if I have something like a sigmoid, the sigmoid is not only going to tell me which side of the boundary I am in, it's going to tell you how far away I am from the boundary, right? And so now, if I do that, then I can make further distinctions, at least in this direction, and be able to compensate for the fact that I have too few neurons in the first layer by having more neurons in the subsequent layers. So the thing is, continuous activation functions, as opposed to threshold activation functions, give you a notion of how far you are from a boundary, which means that you can compensate for reduced width by having more neurons in subsequent layers. Now, for this, the more informative the activation is about how far you are from the boundary, the better you are to be able to actually compensate for lack of width by adding additional neurons in subsequent layers. And so a sigmoid, for example, is not a very great activation because, as you can see, the activation saturates after a little while. So it will tell you how far you are from the boundary for a little distance, and then it saturates. Something like a ReLU, for example, continues to tell you how far you are from the boundary for a very long period of time, all the way up to infinity. So, but only on one side of the boundary. So ReLU is clearly a much better activation than a threshold activation. Or if you have something like a soft plus or a leaky ReLU will tell you how far you are from the boundary on both sides. And so that's going to be more informative. So you can compensate for narrow layers can still pass information to subsequent layers if the activation function is graded, but require greater depth to permit later layers to capture patterns, right? So just adding to our lessons, a single layer MLP can approximate anything to arbitrary precision. Deeper MLPs can achieve the same precision with far fewer neurons. And so deeper networks are more expressive. Now, the neural network, all of this, we're saying, I can compose a neural network to model any function, right? But in order to compose a network to model a specific function, I need to know what the function itself is. Whereas in real life, nobody gives you this function and says, model this function for me. Why would you do it? You just use the original function itself, right? So what you're given are training data. You're given some input-output pairs from the function. So you're only given these red lines, which says, at this input, this is the output. At this input, this is the output. And from those input-output pairs, you have to reconstruct the entire function, like the mesh shown over here. And the way you do it is that you try to sort of train the network, learn the network to compute the function value at these inputs as precisely as possible by minimizing the error, which could, so the network would have some, given any, even if the network has the correct configuration, right architecture, for any setting of the weights, it's going to either overcompute or overestimate or underestimate the function at each point, and you're trying to minimize the total over or underestimation using some loss function. And the hope is that if you compute the function correctly at all of these points, then it's going to be correct everywhere else. But that really won't hold, right? There's nothing stopping the network from learning something ugly like this, where it only learns to predict the correct value at these inputs very precisely and is wrong everywhere else. So how bad is this problem, this business of data under specification? I mean, should we really be concerned? To give you an idea, let's look at a very simple problem. Let's say all I'm trying to do is classify binary inputs in a 100-dimensional space. That's like having a 100-pixel image where every pixel is 0 or 1. It's a really tiny problem. Real data are much, much more complex, right? So if I do that, a 100-dimensional binary input it consists of bit patterns which lie at the corners of a 100-dimensional hypercube. A 100-dimensional hypercube has 2 raised to 100 corners. Now, in order to learn this function properly, that's 10 raised to 30 possible corners, right? The value of the function must be specified at every one of these 10 raised to 30 corners for the function to be learned, right? But then, who gives you 10 raised to 30 training instances? Typically, you may have maybe a trillion training instances. That's 10 raised to 15 training instances. 10 raised to 15 training instances is like, it's going to be off by a 10 raised to 15 in completely specifying this function. It's basically like saying, I'm not giving you any training data at all. So to give you the actual scale of the problem, if I scale down, logarithmically, how many data points I'm giving you per dimension, it's like saying I'm giving you one data point to compute the entire function. And so you give this one data point and say, okay, find me the function from this one data point. And clearly, it doesn't make sense, right? Or to give you an even better idea of how this thing is, suppose I just suppose I had a trillion data points, training instances, for this very simple binary classification problem on 100-pixel data, right? And I scattered these training points on this cube. Now, if you were in a little spaceship and on one corner of this cube, and you began traveling and you were only allowed to travel along the edges of the cube, and you were traveling at any finite velocity, the universe would end before you found your first training data instance on some corner of the cube. That's how sparse your training data are. And from that tiny amount of data, you're asking the poor network to learn the entire function. So the problem is the function is going to, although the network can learn any function given any amount of training data, the actual function that you learn may have absolutely no relationship to what you're trying to learn, especially because neural networks are universal approximators. They can just learn anything. So they're going to learn the most relating possible. Now, you know how to sort of know how to deal with this. You deal with it using regularization. The rationale behind regularization I will not actually go over. But then here's a different way of thinking about it in terms of depth. If I've got a network which is deep, what happens? If I have, say, 1,000 neurons, I can reorganize them as one hidden layer of 1,000 neurons or 10 layers of 100 neurons each. Which one would be better? So what would happen is that each layer is going to learn a function. The next layer is only going to learn a function on top of the function that the previous layer learned. And so long as the activation functions are not arbitrarily, don't have infinite slope, each layer is going to actually end up smoothing the output of the previous layer. And so when you keep smoothing the output of the previous layer, each layer is going to work on something that has already been smoothed out by previous layers and is going to learn a progressively smoother function. As a result, if you go back to a problem of this kind, and here I am going back, this never fails, right? So if I have way too many slides. So where was I? So if I go back to a problem of this kind, right? The problem here is that the network is learning a function which is very steep at each training instance. Smoothness constraints will sort of force it to learn something more shallow. That's what your regularization typically does. And so when you organize your network to be deep rather than wide and shallow, you get these implicit smoothness constraints, which actually teach it to learn something smoother. So here's an example of how that works. This is a toy example. And we are trying to learn the two decision boundaries on the left. One looks like an arrow, the other looks like two squares. The output has to be 1 in the white region and 0 outside. And we've collected something like 1,000 training data points by sampling this little grid. And we've got an optimal architecture in each case. And we've tried to learn the network using every learning trick, Adam, you name it, known to mankind. And the actual decision boundaries learned, you can see, are the ones to the right. They don't look like anything like what you're trying to learn. So this is the optimal network, right? So how does that work? Let's see how this can be handled using depth. So in this example, I'm trying to learn on the left that little board-shaped figure, on the right the bear-shaped decision boundary. In each example, we have 660 neurons. To the extreme top left, we are arranging these 660 neurons as 3 layers of 220 neurons. The next one is 4 layers of 115. The third is 6 layers of 110. And the fourth is 11 layers of 60 neurons. You can actually see that the number of parameters also reduces as you go through the network. And as you can see, that the 3-layer network is not able to learn the boundary at all. But as the same number of neurons, when rearranged to be deep rather than wide, actually learns these ugly decision boundaries quite easily. And so that's one way of doing it. The other, of course, if you increase the number of training instances, with 10,000 training instances, I can learn that there very nicely. For this toy problem, 10,000 is sufficiently enough, but as we saw, that in most cases, you're never going to have enough training data. But the whole point is that depth in the network itself is a way of ensuring that not merely that you have fewer parameters, but even for the same number of parameters, if you rearrange the parameters to be deep rather than shallow, then you're more likely to learn something reasonable than to have something that's shallow and wide. So again, this just sort of comes out of both empirically and out of the math. Now, so what does the network actually learn? Here's the problem. You're given a collection of input-output pairs. You're asked to learn a function, right? Now, when the networks, so for example, if you're trying to learn this double pentagon decision boundary, you would actually be given the boundaries. So you just be given the red and blue dots. And from these dots, you're told learn the boundaries. So you're trying to learn that double pentagon function, which is 1 inside the double pentagon and 0 outside, but you're learning it from only these dots. Except that in the real world, the classes are not going to be so cleanly separated. You're going to have some red dots on the blue side, some blue dots on the red side, and from these you're going to have to learn the function. So what do we really learn? Now let's go back and look at the perceptron, threshold activation perceptron to understand. Now we recall that the threshold activation perceptron just learns this Heaviside function. But suppose I was trying to learn this Heaviside function from training data, then you'd be given training data of this kind, just the red dots and the blue dots. And you'll be trying to learn the perceptron from these red dots and the blue dots, and you'll be trying to learn from those dots the decision boundary shown, right? The step function shown. So how would you do it? All of you are familiar with this concept. If I'm given a single perceptron, you can learn it using the perceptron rule. So you would want to learn the weights and biases of this perceptron such that for the red dots, the weighted sum of the inputs exceeds the threshold. For the blue dots, the weighted sum of the inputs is less than the threshold. Or I can, instead of having a separate, just for convenience, instead of having inputs with weights and a separate bias or a threshold, I can just rewrite it like so. I can say there's an extra input whose value is always equal to 1. And then the weight of that connection simply becomes the bias, right? The threshold. So now, if I rewrite it like so, then we are trying to learn all of these weights such that the weighted sum of the inputs is 1 for all the red, is positive for all the red dots, and it's negative for the blue dots. That's what you'll be trying to learn with the perceptron. And here's how we would do it using the perceptron classification rule. So the weighted sum of the inputs, the boundary itself is going to be a hyperplane that goes through origin. You know this, right? Because you're saying summation wi xi equals 0. That's the boundary. And then we're trying to find these weights such that the all data points from one class are to one side and from the other class they're on the other side. So you want a boundary that perfectly separates these two groups. And here's the perceptron rule that we're all familiar with. You're given a collection of training data points. Each data point is an xy pair. X is the location in the space. Y is the label. It's either +1 or -1, right? Or 1 or 0, depending on how we write it. And the perceptron rule that you're familiar with is you sort of initialize the weight somehow and then begin checking every data instance, saying, is this correctly classified? If it's a positive instance that is misclassified, then you're going to add that input to the weights. If it's a negative instance that's misclassified, you're going to subtract that input from the weights. How does that logic work pictorially? So here's what the actual thing does. Now, you're just given this collection of data points. You'll initialize your weights somehow. The weights would give you some hyperplane, and maybe like this red line. And then you begin classifying your data instances. So you find, for instance, that you would find this, say, this is your initialization. You find that this blue dot is being misclassified, right? It's being misclassified as, let's say the blues are the positives. It's being misclassified as a negative instance. So the weight vector is shown by the blue arrow. The boundary is always perpendicular to the weight vector. So what you would do is, that's the data instance that is misclassified. You're going to, it's a positive instance. So you're going to add it to the weight vector to drag the weight vector towards that instance. And then when you add it, The new weight vector is going to be given by that blue line, the new blue line, and the new decision boundary is going to be this guy, which is perpendicular to the new blue line, right? And now using this, you go back and continue checking all of your data instances to see if any of them is misclassified. And then maybe you find that this red instance, which is a negative instance, is misclassified. So it's a negative instance, that's the misclassified instance. So you subtract it from the weight, which gives you this new weight and this new boundary. And that's going to, and so you keep repeating this process. Every time you find a positive instance that's misclassified, you add it to the weight vector. Anytime you find a negative instance, you subtract it. And eventually, if the data classes are linearly separable, you're going to end up with a decision boundary that perfectly separates the two classes. And in fact, it's very easy to prove that if the classes are linearly separable, this is going to converge in a finite number of steps. The number of steps is upper bounded by the ratio of the length of the longest vector and the margin of the optimal boundary, the square of the ratio. Anyway, here's what is this problem. When classes, I mean, that entire rigmarole was meant to bring across a point that when the classes are linearly separable, you can find an optimal boundary that separates the classes with very little effort, using 3 lines of code, or even less, in basically linear time. But that same algorithm will not work if the classes are not actually linearly separable. So in the real life, classes are not going to be separated. You're going to find some red dots hanging on top of the blue regions. You're going to find some blue dots sitting on the red side, because there are always some points which look more like the other class, right? So here, the algorithm will not converge because there is no line that cleanly separates the two guys. So how do you deal with this? Let's back off to a one-dimensional example to get an idea of how one deals with it. In the case of the one-dimensional example, the inputs are just single features, x. The output label is either a 0 or a 1. So all the blues represent one data class, all the reds represent another data class. And then if you were trying to learn a single perceptron for a unidimensional input, the perceptron is basically a threshold. If the input exceeds a threshold, output is going to be 1. If it's below the threshold, the output is going to be a 0. And clearly, there is no threshold that perfectly separates the reds and the blues over here, right? Now, instead of a single perceptron, suppose I train a multi-layer perceptron. An MLP, as we know, is a universal approximator. It can model any function. So if I give you this training data, there's absolutely nothing stopping the MLP from learning this crazy green function. But do we really want this function? This clearly doesn't make sense, right? This seems broken. Now, even if you assume that, okay, you're willing to live with this nonsense, things get more complex. For instance, suppose I have training data where for the same value of x, some training instances have y label 0, others have y label 1. In this case, what would you want your network to output? Do you want it to output a 0? Do you want it to output a 1? Or do you want it to output the fraction? So for instance, if I have 10 training instances which are 0 and 90 which are 1, do you want it to output 1 because the majority are 1, or 0.9 stating that 90% of the training instances at the x have the label 1? Clearly, the 0.9 is more informative. It's also more useful, right? That's what you would want. So this makes more sense. But then let me change things a little bit, right? So what is this 0.9? This 0.9 is your best guess for the a posteriori probability of the class 1, given the input x. It says for this value of x, 90% of the inputs, 90% of the data have the label 1, right? But then suppose all of my training data instances are not exactly the same value. They're all off by 10 raised to minus 17. So the limit of arithmetic resolution. At this point, suddenly does it become sensible to, for my function to begin jittering up and down? It doesn't, right? Things haven't changed substantially. Even here, you want the most reasonable output, which is for any x in that range, you want the output to be 0.9. So how did I decide what is the range of perturbation which I find acceptable, where I want the same output value? So here's a different way of thinking about it. Hypothetically, let's say that at any point, I don't look at just that point x, but I look at a small window around that x. And for that point, I'm going to be plotting the y value as the fraction of inputs within that window which have the label 1. So over here, that y value is going to be 0. But then when I come here, I begin seeing some instances of y equals 1. So the fraction is going to be greater than 0. And as I keep going from left to right, eventually it's going to become all ones, right? And so this is the kind of function that I would actually want the function to model. This makes more sense when I begin looking at it from a rational perspective. What makes more sense? And what does this function actually give me? This function is an approximation, a guess of the a posteriori probability of the class 1 given the input x. And that has this shape. And this function is your famous sigma. You're all familiar with it. Your logistic function, your softmax, they're all exactly this function. And so you can see that it has a standard form, it has a form 1 over 1 plus e raised to minus w0 plus w1x for and you can see that if the argument of the exponent is a large positive number, then e raised to a minus of a large positive number is basically 0. This becomes 1. If the argument is a large negative number, e raised to minus of a large negative number becomes infinity. 1 over infinity becomes 0. So to the extreme left, it's 0. To the extreme right, it's going to be 1, right? And then our job, so when you think of the perceptron using a softmax or a logistic activation, this is what it is. It's actually capturing, modeling the a posteriori probability of the class 1 given the input. But now consider this two-dimensional problem again. In the two-dimensional problem, you're going to have they're not linearly separable. So you're going to have some green dots on the red side, blue dots on the red side, red dots on the blue side. In the two-dimensional case, what does that function look like? It's still going to be a sigmoid, but now it's like a sheet, which goes from 0 to 1. And that is going to actually give you the a posteriori probability of the class 1 given the inputs. Right? Yet, although the function is not a linear function, this is a linear classifier. Why so? It's like this is the sheet, but then if once I've computed the function, if I'm asked to take a hard decision, is the class 1 or is the class 0? What I will do is to compare this function value to a threshold. And if it exceeds the threshold, I'm going to say it's 0, otherwise I'm going to say it's 1, otherwise I'll say it's 0, right? And so the value of the axis where the function exactly equals any given threshold is going to be a hyperplane. So for any threshold, the actual decision boundary is going to look like the decision regions are going to be separated by a hyperplane. So although the function is a curve, as a classifier, it's a linear decision boundary, it's a linear classifier. Now, how do you estimate this model? Here is the function again. This is your logistic function. It's a softmax, it's a sigma. It goes smoothly from 0 to 1, right? You're going to try to learn this function from xy pairs. Now, when I drew that little oval, those of you who are paying attention would have thought, how did I decide how large that oval was to decide to put the dot with the fraction, which indicates the fraction of inputs within that region that have the value 1? I don't. So here's what I do. This is the probability of the class 1 given the input x. So 1 minus this value is going to be the probability of the class 0 given the input x. I can write these both of these using one common formula. So P of y equals 1 given x is going to be 1 over 1 plus e raised to minus of w0 plus w1x. So 1 minus of that is P of y equals the other label minus 1 given x, which ends up being 1 over 1 plus e raised to plus w0 plus w1x. So I can write both of them jointly using a single formula, which is 1 over P of y given x. There's 1 over 1 plus e raised to minus of y times w0 plus w1x. And you can see, you can plug in y equals 1 and verify it gives me this formula. You can plug in y equals minus 1 and verify that it gives me this formula. Easy enough, right? And now, if I'm given a collection of training data points, the total probability, joint probability of all of these training data points is going to be the product of the probabilities of the individual data points, which is going to be the product of P of y given x times P of x for all of my training instances, right? In P of y given x, we saw was this formula here for the sigmoid with the argument multiplied by y times P of x. Straightforward. And if I take the log of the entire training, of the probability of the entire training data, that's simply going to end up giving me the summation over all training instances of the log of P of x minus the summation over all training instances of the log of the denominator of the sigmoid. Now, what is the point of all of this? If you look at this first term is not a function of the parameters of the sigmoid. Only the second term is a function of the is a function of the parameters of the sigmoid, and this is a standard statistical model, right? I'm computing the joint probability of all of my training data. So if I want to do a fit of my model, I'm going to do a maximum likelihood fit. I'm going to try to find the W's, the weights that maximize this joint probability. And so that's simply going to be argmax of the total log probability of the training data, or argmin of the negative of the log probability of the training data, which, so again, the log probability of the training data had a minus over here. So it's argmax of this negative term, or argmin of just the term within the summation. And this is exactly the same as minimizing the cross entropy between the desired output y and the actual output of the sigmoid. Can't be solved directly, it needs gradient descent. But what is the point of all of this? I don't expect you to memorize the math. The point is that when you use gradient descent and you minimize the cross entropy between the output of the network and the target output of the network, the target output of the perceptron, what you're really performing is maximum likelihood estimation of the parameters of the perceptron. So you may not be aware of it or you may not be thinking about it, but you're actually performing statistical estimation when you train your perceptron. But that was for a single perceptron, right? Over here, we're talking about a single perceptron with linear decision boundaries. What happens when you have something more crazy, like this, relatively simple double pentagon decision boundary, where again, you're likely to have some red points on the blue side and some blue points on the red side? What happens here? So before considering that, let's look at the separable case. Let's have the simple situation where I have only red dots inside the pentagonal regions and only blue dots outside. And I'm trying to learn the boundary, right? So we know that this double pentagon decision boundary can be modeled using this simple network. I have one subnet for the first pentagon, a second subnet for the second pentagon, or the outputs, right? What is this final neuron? The final neuron is once again a linear classifier. We saw that a single perceptron is a linear classifier, correct? So if a perceptron is a linear classifier, and if this network is doing a perfect job of distinguishing the red dots from the blue dots, then it means that at that point, the inputs to the final perceptron must be linearly separable, right? So what this in turn means is that this y1 and y2, if you plotted y1 and y2, you would find that y1 and y2 are linearly separable, otherwise the final perceptron would not be able to separate them. So in other words, this portion of the network, I can think of the entire network as having two components. The lower portion is this box, which is a transformation which transforms the input until the classes go into a new feature space where they are linearly separable. And now the final perceptron is actually able to perform linear separation of these classes. And so the network can be thought of as two components. The rest of the output linear classifier and the rest of the network, there is a transformation that converts the non-linearly scattered distributed data into linearly separable classes. And in fact, once you view it this way, if I give you linearly separable data, there are different kinds of classifiers you can put in, like an SVM, for instance. You could even put in a max margin classifier. So, and now this is true of any sufficient architecture. It didn't have to be just this exact optimal architecture. If the network is capable of classifying this data perfectly, then it means that the network until the final output layer is a transformation that makes the data linearly separable. And the output layer is the linear classifier that separates the data. So in this process, we've actually learned, if you learn such a network, we've learned a magical box that learns to make the data linearly separable. So mathematically, if you can think of the entire network as this component, it has this output, if it's a logistic function, is a linear classifier, is a sigmoid working on y1 and y2. And y1 and y2 in turn are the outputs of the lower portion of the network, which are represented as f. And so the entire network is in fact a sigmoid classifier working on a non-linearly transformed version of the input, where the non-linear transform tries to make the classes maximally linearly separable. So, but that's the case where the classes are separable, right? What if I have data of this kind, which is more typical? What happens is the same logic still holds. If the network is properly trained, the rest of the network until the final layer is basically a function that tries to transform the data until the data are as linearly separable as possible, given the constraints of the network. And then you have the final linear classifier, the sigmoid, which actually computes the posterior probability of the classes, given this transformed data. Now it's a posterior probability. So what this means is that this entire network is essentially a statistical model that computes the a posteriori. If you're using a sigmoid output activation, this entire network is a function that computes the a posteriori probability of the classes given the input. And the feature extraction layer transforms the data such that the posterior probability can now be modeled by a logistic. So even in a case such as this, the output of the network eventually is simply going to, it doesn't matter whether you're giving f of x or x. The output of the network, so long as f of x is a one-to-one function. So the output of the network is computing the posterior probability of the classes given the input. And so a neural network is basically a statistical model, especially if it's trained using a cross entropy loss. It's a statistical model that computes the posterior probabilities of classes given the input. So it's not just a magical function. It's a statistical function. More precisely, it's a statistical estimator. It's not computing a function. It's computing a probability. It's computing the posterior probabilities of classes. And your training algorithms are actually performing maximum likelihood training of the parameters of this statistical function. So an MLP actually comprises two components: a feature extraction network that converts the inputs into linearly separable features or maximally linearly separable features. They will not be separable. And a finer linear classifier that operates on these features to compute the posterior probabilities of the classes. So fine, we know what happens at y1 and y2, right? So we know that y1 and the network until here basically converts the data into linearly separable features. What about the rest of the network, the stuff below? What happens over there? There are several hypotheses for these. But the basic, remember that the final output layer needs linearly separable features, right? So the rest of the network is basically a function that incrementally keeps making the data more and more and more linearly separable. And so here's a nice illustration of how this works. In this case, we are trying to capture this figure is kind of distorted. We're trying to capture the circular decision boundaries on the top right using 1,000 training instances. The network that we've got over here is a very simple network, which has just got one hidden layer of 3 tanh activation neurons, and then a final output layer. And then remember what happens. When I have a hidden layer, the first thing that happens is, if you've implemented these networks, you take the input and then I'm going to compute an affine value, right? A linear layer which computes a three-dimensional vector from these two-dimensional inputs. Then this three-dimensional vector is put through a tanh activation, which is a nonlinear transformation. Then at the output neuron, from this three-dimensional vector, I compute a one-dimensional affine value, and then that's put through my segment, right? That's what computes performs the final classification. So in this figure, this is the data, and this guy here is the output of the first affine value. So, if you've got the network is, I don't know if I've got the figure here still, I don't have it. So here's what happens. The figure to the extreme left is showing the loss, the top left, but here's what happens. I start off with this circular decision boundary in two-dimensional space. The first step, when I first compute before my activation, it takes this two-dimensional plane and positions it in three-dimensional space and finds the right orientation for it. Then the tanh activation sort of takes this sheet and distorts it point by point using the tanh activation. So you can see what happens when it gets distorted. Then at the next layer, this distorted thing is projected onto another line, which collapses it into a single layer. And you can see that at that point, once you collapse this guy, the red, because the center is stretched out, the red and the blue become separate. And now I can just use a threshold to separate out the blue from the red. And you can see how this actually ends up learning the circular decision boundary. So you can see as you go through the data, it gets continuously warped until it becomes more and more linearly separable. This may be a bit too simplistic, but here, this is from CIFAR. This was in this case, it's 11 layer network, 11 hidden layers. And the different colors represent data from different classes. We projected the activations onto 2 dimensions just for illustration. And you can see that initially, when the training begins, all the data are not linearly separable. But then as the training progresses, you can see that the different classes, as you go through the layers, the classes become more and more linearly separable. And in fact, by the time the data comes to this 9th layer, all the classes are already linearly separated. The subsequent layers are not really doing very much. And so in fact, when you train very deep networks, this is a 2-dimensional projection. You can see how this happens. I actually also have a 3-dimensional projection for the same example. And you can see how by the time you get to the 9th layer, the classes are separable. and then the subsequent layers are not really doing very much, right? So when you train deep networks, what you will find is as the data progresses through the layers, you can see how the classes are continuously separated, linearly separated, and at some point the classes will become linearly separated. The rest of the network is not really doing very much. So for example, if you were to train a deep network for a task, and then you were asked to make the network smaller, you could just train the network, then throw away the final, 20 layers or whatever, because by that point the classes are already separable. I can just plug a classifier on top of it and then get the same job done. So, but the point being that the layers sort of incrementally keep increasing the, making the classes more and more separable, right? So we spent all of this time looking at the network as a classifier, it learns features, it's computing Boolean functions, you can compose everything using Boolean functions, but really the final classifier is a linear classifier, so the rest of the data, the network has to make the network, the classes linearly separable, right? And so finally, once you make them linear, so we found that as what the network really does is incrementally increase the linear separability of the classes. And in fact, when you train the network properly, if you train it long enough and hard enough, eventually you will find that way before you get to the end of the network, the classes have already become linearly separable. And the network, the actual portion of the network that does the job is much smaller than the final network itself. Well, that's fine. So we've learned the networks, what the network learns here. We've learned what these regions, this portion of the network does. But what about these individual guys? What do they learn? For that, let's go back and look at the perceptron again. Now we've seen this, I've explained this earlier also. What do the weights tell us? Each perceptron is looking at an inner product between the weights and the input. It's comparing it to a threshold. And we've seen that basically what this means is that it's computing essentially the cosine between the weights and the input. And if the cosine exceeds a threshold, which means that the angle is lesser than a threshold, the perceptron fires, otherwise it doesn't fire, right? So given this, we saw that essentially it's just a correlation filter. It's trying to compute the correlation between the input and the weights. You could in fact handcraft your network to detect specific patterns. But there's a flip side to this. The flip side to this is this. If I train my network for a task, each of the first layer neurons is actually detecting a feature from the network, right? From the input. It's going to fire if a specific feature has been found. So if I train the network for detecting if you've seen those old LED watches or calculators, they have an LED pattern. And they actually use these LEDs to show numbers, right? So if all I'm doing is training a network to detect if this LED pattern represents a digit or not, then you expect that the first layer neurons are going to be detecting features that clearly distinguish digits from non-digits. So maybe finding all of these horizontal and vertical bars which compose digits, or maybe finding diagonals which clearly indicate the presence of which clearly indicates that it's not a digit, right? It's going to be detecting these patterns. But then here's something. If I have found certain features, right? Think about this. This first neuron is trying to detect a bar on top. How is it detecting a bar on top? It's detecting a bar on top by having a weight pattern, which is 1 at the top and 0 elsewhere, right? The weight is exactly the same pattern that the neuron is actually trying to detect. So if this neuron fires, I know that that pattern is present in the input. So based on the firing of these neurons, suppose I try to reconstruct the input. I can just check the first neuron, see if it is fired, and then just draw its weight pattern and say, I know this pattern is present in the input. right? Similarly, for the second neuron that's looking for this vertical bar to the right, I can check if this neuron has fired. If it has fired, I know that that vertical bar, that's the pattern of weights, right? So I can just draw the pattern of weights and say this pattern of weights is present in the input. And so I can literally reconstruct the input by just combining the weight patterns of all of these neurons together to of all the neurons that did fire. So this I can sort of reconstruct it by saying I'm going to be multiplying the output of each neuron by its own weight pattern. If the neuron has fired, that's going to give me a 1. So that weight pattern will go in. If the neuron didn't fire, the output was 0, so its weight pattern will not be included, right? And I can reconstruct the input by just putting together the weights of all of the neurons that did fire. And it should, in theory, recompose the input. Now, will it actually recompose the input? In this example, it won't, because in this example, I've tried to train a network that can detect if the input is a digit or not. So I expect the feature detectors only to learn those patterns which are important to distinguish between digits and non-digits. So the reconstructed input is only going to have those components of the input. If I wanted to, this will only retain digit-like, obviously digit-like, or obviously not digit-like features, because the rest are irrelevant and will be lost. But I can train the network to predict the input itself more explicitly, right? In which case, instead of trying to perform digit classification, I can just say reconstruct the input. And this is what we call an autoencoder. All of us are familiar with it. So there's a lower portion until the neurons, which learns to detect significant patterns in the input, and the recombination, which puts these patterns back together to reconstruct the input. So what does an autoencoder do to understand what the neurons, the networks, individual neurons learn? Let's look at what an autoencoder itself learns. And let's consider the simplest autoencoder. The simplest autoencoder is just a single neuron. So if it's a single neuron, it's going to have an input, it will fire or not, and then you're going to predict the output as the weight pattern of the input itself. So if you think of this now, just for this to make it easier to understand, let's assume that this doesn't have a threshold activation, it's linear. It's just passing the input through, right? So in this case, what will this network learn? What will the single neuron learn? The output of this neuron is simply going to be the weight times x. The output here is going to be the output of this neuron, which is the weight times x times W transpose. So x hat is W transpose Wx. The input is x. So the error is going to be x minus x hat squared, which is x minus W transpose Wx squared, the squared norm. We're trying to minimize this error. And those of you who are familiar with this, who recognize this, will know that this is basically just the standard optimization for principal component analysis, PCA, if the data are zero mean, right? And so what will this simple model learn if I've got an autoencoder? This single neuron is simply going to learn the first principal component of my training data. Now, so here is the interesting thing, right? The output is always going to be some W transpose, some value. So regardless of the input, the output is going to be some scaling of W. So regardless of the input, the output is going to be something on this black line in this case. So it's always going to be just some value on the principal direction, right? So any input, when I put an input through this network, it's going to take the input and map it onto a point on this principal axis, shown by the black line. If I just have only one neuron in the network. So here, why is everything just on this line? That's because the reconstruction portion of the network is taking in the output of this portion of the network, the lower portion of the network, which I'm calling Z here, and it's computing W transpose times Z, which is just, some scaling of W, right? So the output is, or regardless of the input, the output is going to be something on this blue line. And simply varying this value Z over here is always going to give me something that's on this blue line. And this will happen even if this output, the weight of the reconstruction portion of the network is not exactly W transpose, but some other vector. So if I learn two separate vectors, one for the reconstruction portion of the network and one for the initial lower portion of the network, the output is always going to be some extension of U transpose, and the reconstruction weight, this guy over here, that one is going to be the principal direction on the data. So the reconstruction portion of the network is what is capturing the principal component of the data. Now that's with one dimension. Suppose I have a whole collection of hidden neurons, a network of this kind. What happens? Here, again, the same math holds. If all of the hidden neurons have a linear activation, the output of the hidden neurons is simply W times X. So W is now a matrix. The reconstruction is W transpose Y, which is W transpose WX. So if I minimize this error, this is just again principal component analysis. And so what the network is actually learning is the principal subspace of the data. So if you're training an autoencoder with linear activations, the autoencoder is going to learn the principal subspace, and the reconstruction portion of the network can only reconstruct the principal subspace, shown by the pink sheet over here. Regardless of the input, the output is going to be on the pink sheet, right? Now, so this is still PCA. Now, still PCA. So this is terminology that you would have encountered. The portion of the network that computes the initial hidden representation of the data, that's called the encoder. The portion of the network that reconstructs the data from this hidden representation, it's called the decoder. And so this guy here is going to, the lower portion of the network is going to find the location, the coordinates on the plane of the data. The coordinates here in this case would be two-dimensional for this example. And the decoder portion of it is going to reconstruct some vector on the principal subspace using the coordinates. Now, that's assuming that all of the activations are linear. What happens if the activations are non-linear? As we saw in the case of the time-age activation, non-linear activations will bend your sheet, bend your data, right? So bend the subspace. So when the decoder and the hidden layers have non-linear activation, what the network is actually doing is computing a curved surface, a non-linear surface that captures most of the data. And so it's actually performing non-linear principal component analysis when you learn an autoencoder with non-linear activation. So here's what it looks like. The autoencoder is going to have an encoder and a decoder. The decoder, again, is going to construct the non-linear manifold, which captures most of the data. The encoder is going to find the position of this manifold. And so the encoder finds a position, the non-linear reconstructs the surface, and it puts the data on some specific position of this manifold. And so the deeper these decoder networks, the more complex the manifolds it can learn. Now, how does that work? Here's an example of data that lies on a spiral. Now, these are two-dimensional data. And we've tried to learn a fairly complex autoencoder using this two-dimensional data. Now, this decoder, again, remember the decoder can only construct data on the principal manifold, except in this case, the principal manifold is not linear anymore. And the encoder is finding a position on it. So when you train an autoencoder using this spiral data, the output of the decoder is actually this guy over here. So ignore the blue portion for now. So what happens is this decoder, it turns out, learns to reconstruct the spiral. Now, it's not as intuitive as you would like it to be, because I've provided some training data, and it learns the structure of the data for in the range of the training data, but outside the range it learns, there's no guarantee that it will be useful. So here, for instance, if I take the decoder and provide it with z values out here, which were not seen in training data, then the way it extends the data is shown by this blue line. So it's not continuing to reconstruct the spiral even outside the range of the training data. But within the range of the training data, it actually reconstructs the spiral. Or here is another example where the data lie on a sinusoid. And you can see how the decoder actually learns the underlying curve that the data lie on, but only within the range of the training data itself, right? So the autoencoder, as we can see over here, is so there's a network where a part of the network learns the surface, the high dimensional manifold that the data lies on, and the encoder portion of it learns a position on this manifold. The key piece is this, that if properly trained, this decoder is only ever going to be able to reconstruct data that lie on the principal manifold of the generate points that lie on the principal manifold of the data itself. So that means it makes it an excellent generator of the distribution of the training data. What do I mean here? I mean, here's an example, right? If I trained, for instance, remember, I trained this, I started off with this example of digits, right? If I train an autoencoder using digits, then all digits are going to lie in some manifold, nonlinear manifold of high dimensional space. Now, if I take the decoder of this autoencoder, regardless of the input that I give the decoder, the output must look something like a digit, because it's only able to reconstruct data on the digits manifold, right? Or here is an example. In this case, we actually trained an autoencoder on a saxophone, and then you take the decoder and you feed the decoder with some random input and see what the output it generates sounds like. And so here's, if it plays, it actually ends up generating something that sounds like a saxophone. If I give it another random input, so I have not taught it anything, right? I've not given it any information about saxophones or whatnot. All I've done is give it training data only using, which are all saxophone data. Then if I feed the decoder with random inputs, the only things that is capable of generating kind of look like sound like saxophones, right? Or here's another example. This is this one was trained using clarinets. And so once you train it, it's actually learning. So it's learning the topology of the subspace that clarinet data require. And so now if I just excite the decoder using any odd input, and the only thing it is capable of generating are going to sound somewhat like clarinets. So what this means is that in the process, even though you can't really, it's hard to interpret what the individual neurons might be learning after the first layer or so. As a conglomerate, the decoder portion of the network is only able to, the encoder portion of the network learns a position on the manifold for the data, and the decoder is only able to generate data on this manifold. So the decoder by itself ends up being a dictionary for the kind of data that the training data lie on. And so I'm going to actually close. I'll close slightly early. I know all of you guys are sleepy. You're waiting for lunch. So I'll close this with a very cute little example of how this can be put to use. nothing new, it's trivial. It's like 10 lines of Python code with PyTorch, and a little more. There's input and output as well. But I'm going to try to do something with sound separation, right? We're going to use a standard dictionary-based technique. Now, suppose just how does dictionary-based techniques for sound separation work? So how do dictionary-based techniques for generation? Suppose I have a dictionary where any entry in the dictionary represents an instance of the kind of data I'm trying to generate. For example, I could have a dictionary of guitar notes. Anytime I excite it, it's going to produce a guitar, right? So then I could have a dictionary that composes only guitar notes. And then similarly, I could have a dictionary that when excited only generates drum sounds, right? So now if I gave you a mixed recording that included guitars and drums, and I asked you to separate the guitar from the drum, then you would start off, you would have a guitar dictionary, you would have a drum dictionary, and then you're going to say what combination of entries from the guitar dictionary and what combination of entries from the drum dictionary, when summed, is going to give me an output that sounds like my mixed signal. If I can find out this combination, then I know what the guitar component was, what the drum component was, I can separate that. Very easy, if you know how to do this, right? The key piece is being able to compose a dictionary that can only generate guitars, or compose a dictionary that can only generate drum sounds. And what we just found was that autoencoders, when trained properly, give you the decoders of autoencoders, give you exactly such dictionaries. So we can actually use the entire autoencoder-based framework for just this purpose. I could train an autoencoder on my dictionary, on my guitar sound, on a collection of guitars. I could train a separate autoencoder on a collection of drum recordings. And now the decoder of my autoencoder for the guitar can only generate guitar-like sounds. The decoder for my drums autoencoder can only generate drum-like sounds. And now when I get a mixed signal, I know that there is some excitation, some input R to the guitar decoder and some other input to the drum decoder, such that if I sum the outputs of these two decoders, that output with the sum sounds like a mixed recording. So based on that, I can now compute, I can use my mixed recording, the original mixed recording X, and now I can use backpropagation and all the standard estimation tools. Try to estimate I1 and I2, the inputs to these two decoders, such that the sums of the two decoders when added, the outputs of the two decoders when added, give me this mixed recording, or the closest approximation to the mixed recording. And once I do that, then I can, this output here, the sum of the two, is going to give me a pretty good approximation to the mixed recording. But the output of the first decoder is going to give me a good estimate of what the original guitar sounded like. The output of the second decoder is going to give me a good estimate of what the original drum sounded like. And hopefully I've done managed to get some separation. So let's look at some examples of how that works. Okay. So that's a mixed recording, two main instruments. So this is again, point is, and just to convince you that it's not lying, it's that it didn't, here's the original. So it does a pretty good job. Both of them are wind instruments. No one is a string instrument, but still very similar sounds, right? And what we are finding is that the network is actually learning the topology of the manifold that the data lies, or seems to be learning it so that, it's actually able to reconstruct the individual components to generate that signal. So anyway, I'll stop right here. We've spent 3 hours, or the better part of 3 hours, minus early completion and the breaks due to my slides, on trying to look into what neural networks actually do. What we've done is we've seen that neural networks can model any Boolean function. They're basically models of the brain. They can model any Boolean function. They have the ability to model any Boolean function. They have the ability to model any classification boundary at all to arbitrary precision. They have the ability to model any real valued regression to arbitrary precision. But in order to model anything, they need to have they need to be large enough. So when a model has fixed depth, it will have to be very wide for it to model a function. You can compensate instead. It's much more parsimonious to make the model deep as opposed to wide. But the optimal depth depends on the complexity of the function that you're trying to learn, which is often not going to be knowable. So the conservative thing to do is to just make it as deep as you possibly can. But we also saw, that said, we also saw that the model, once the model is actually able to do some job, or partially able to do a job, it actually has two components to it. You can think of it as a combination of a transformation which takes your input. In the case of classification, you can think of it as a combination of a function that takes your input and converts it to some linearly separable into some space where the classes are linearly separable, and then a final layer is basically just a linear classifier. Then we further looked into that, and we saw what happens within the lower this complex function. We saw that layer-wise, what the model actually increasingly it increases the linear separability between the classes. It transforms and distorts the data by taking it into a higher dimension and collapsing the higher dimensions incrementally till the classes become linearly separable. And you have no worries about over-engineering your network, because if the network is too deep, is much deeper than you need it to be. All that happens is that the network learns to make the function, the classes linearly separable well before the end of the network, which is not a bad thing. It could also at the end throw away the final portions of the network. We also saw that the intermediate portions of the network represent neurons that capture basic patterns in the inputs, starting with simple patterns, which become increasingly more complex as you go through the network. And of course, for all of this to work, you need the earliest layers of the network to be sufficiently diverse to capture all the patterns, all the relevant patterns in the input, because if they didn't, then you're going to lose patterns, then you will never be able to make any predictions based on them. You can compensate for them to some extent by having graded activations, but the basic problem still remains. So the network needs to be sufficiently deep and sufficiently wide. We also found that if we do a good job of learning these patterns, in fact, these patterns are enough to reconstruct the input. And so we close by saying that this is so powerful an idea that the network can actually be used to capture the high dimensional manifold on which the data lie. And the fact of the matter is, it doesn't matter what kind of data you look at. If the data are structured, they lie on a low dimensional manifold in high dimensional space. If they didn't, there would be noise. The reason we exist is that we live in low dimensional manifolds in high dimensional space. And so that structured nature of it, and the ability of the network to learn the structure, can also be used for other purposes like reconstructing data or things like some of my favorite example of separated musical instruments in this. But I'll stop right here and take any questions. You can. Yes.
So basically, from what I understand, you can still train a deep architecture with linear activation function.
No, because if it's linear, then the adding more layers is the same as collapsing it to one. So when you don't have non-linearities, having 1,000 layers is the same as having one layer.
So how come the perceptron and the multi-layer perceptron can learn its slow function?
So because the perceptron's activation is non-linear, it's a linear classifier, but it's a non-linear function, right? There's a difference. Yeah.
So you mentioned, right, when that the last two layers of the network might is already be too much, right?
They're not too much. It's just that when they're properly trained, they're not doing anything extra. Yeah.
Oh, okay, so ideally computation-wise.
Yeah. So you could throw them away and just retrain your stuff. Yeah.
Doesn't make a difference to throw them away.
After training.
Yeah.
Yeah. I mean, you would have to fine tune your output layer, right? But yes. In fact, it's a common trick that when you start off by training a deep network, then throw away, layers starting at the final layer till you get something where throwing away the layer hurts. Yeah.
Everyone seems to be hungry.
Yeah.
So in your example of generating new data with a decoder, right? You need to sample from some distribution
Correct.
in the bottleneck layer. So where do you take the distribution from?
So if I said training data in my music example, I train those on instances of music. So the idea being that when I train them on real data, they are samples from the real distribution. So the training data, anytime you have a valid collection of training data, they are actually samples from the distribution of the data. That's the assumption we always make when we work with these models, right? I mean, there could be other kinds of, they could be purely synthetic too, but regardless, so long as the training data are drawn from the distribution, you will learn the structure. And that's basically the same concept that you learn in all of these generative models, VAE, scans, you name it. Yeah.
Hello, thank you for this great talk. This is a question more comparison between two fields. I don't know much about the second field. I'll say as understood at kind of beginning of the process learning, the network is learning a manifold.
Yes.
Which is described by the data point.
Yes.
So I know that there is the field of topological data analysis based on algebraic topology, which is also learning manifold based on training data as neural network. So my question is, what differences or what exists between this approach and the topological data approach?
There isn't any difference. So the point is this: most of the theorems that you see that prove neural networks to be universal approximators and such like actually draw on those ideas. What we have is a computationally feasible model for it.
So concerning the computational approach via the algebraic topology setting, is it more difficult to use it in a computational manner than these neural networks?
So the neural networks are very high dimensional model, right? They're stacked. I mean, so the math that you would do, you're just doing basic algebraic topologies, nowhere comparable to the complexity of the models we have in neural networks. But essentially, they're doing the same thing.
Hi, thank you for the great talk. I wanted to ask something about your example with the digits and the encoder-decoder. So in the example that you showed, it seemed like each neuron will learn like a representation of some part of the input. And it seems like it's disentangled in a way, like each neuron is responsible for a specific type or feature or something. But I wanted to ask if this is really what happens in practice, because I would expect that they will be shared across different neurons actually.
So in principle, yes, that's what should happen. In practice, if they don't, it doesn't quite disentangle, because if they're learning, there's nothing stopping two neurons from learning the same thing, right? So naive learning doesn't guarantee that they're disentangled. It's just that they are enough to be decomposed. This is actually a standard problem that many researchers have tried to address over the years. And what Scott Harmon calls the herd effect. In that you find an error, all the neurons will try to fix that error. Then one of them fixes it, and all the remaining neurons will try to fix some other error, including the first guy. So there's a lot of duplication that happens, which means that they're not really disentangled because they're not doing completely separate things. And which is why when you train neural networks, for example, in my double pentagon example, I need only 10 neurons in my first iteration. But if you try to train a network with 10 neurons, it will not run the double pentagon. What happens is 4 of those neurons will end up running the same line. So typically what you will do is to have like 100 neurons. And the hope is that if you have a sufficiently large number of neurons, by sheer luck, between them they will learn all the boundaries. At which point you can throw away, that's what a lot of pruning approaches do. You throw away all the things just simply repeating work that other guys did. So yeah, it doesn't really disentangle. It should be in principle. In practice, learning is a problem.
Thank you.
No more questions.
So, hi. So what do you recommend when we have thank you.
What do you recommend when we have a variable like an input that has variable length, like text, for example? A lot doesn't work yet. So would you recommend that we have like a lot of layers, as much as possible, neurons on the first layer, or is there any logical solution?
So we use those as time series, right? But then when you're modeling time series, you're really modeling them as a sequence of inputs. And the model that optimal model that depends on the complexity of the patterns in the individual samples that you're looking at rather than the totality of it. You're sort of hoping for the recurrence to capture more of that, right? But if you're using convolutional kind of models, again, it makes sense. So here's the thing. Are you capturing enough information to reconstruct the input? So what happens is when you're trying to learn a model, let's say I'm learning a CNN, then if I've got an input which is say 10 channels, 1000 cross 1000, then I've got 10 million variables in my input. So if the output of the CNN also has 10 million linearly independent variables, it has all the information, it potentially has all the information about the input, just rearranged. So long as we have that kind of structure, we retain that kind of structure, we are retaining enough input, enough information for downstream layers to perform complex tasks. The moment the number of parameters is such that you lose information, then the issue that comes out and talk about sort of kicks in. You lost information, it can never be recovered. Right? Thank you.